The universe is often described as a grand cosmic symphony, but what if I told you that this symphony is composed of 40 universal patterns, threads woven into the very fabric of space and time? These patterns are not just abstract concepts, they are the invisible forces shaping everything, from the tiniest particles to the vast expanse of galaxies. Today, we're going to unravel these patterns, exploring their origins, their role in the cosmos, and how they might hold the key to understanding reality itself. By the end of this video, you'll see the universe in a whole new light, a tapestry of interconnected rhythms and harmonies that could redefine what we think we know about existence. So, let's dive in and discover what these 40 universal patterns reveal about the deepest mysteries of space and time. Imagine the universe as a grand, intricate tapestry, where every thread is meticulously woven together to create a breathtaking design. These threads are what we call universal patterns, the fundamental structures that form the very essence of space and time. Think of them as the cosmic blueprint, the invisible framework that gives shape to everything we see and experience. From the way galaxies spiral in the vastness of space to the delicate dance of subatomic particles, these patterns are everywhere, quietly governing the order of the cosmos. But here's what makes them truly fascinating. They're not random or chaotic. Instead, they follow precise mathematical and physical laws, like a symphony composed by nature itself. Whether it's the Fibonacci sequence seen in the spirals of a galaxy or the fractal geometry found in the branching of a tree, these patterns are repeated across scales, from the quantum realm to the vastness of the universe. They're universal in the truest sense, appearing in the smallest particles and the largest structures, binding the cosmos together in a harmonious rhythm. What's even more intriguing is that these patterns aren't just static designs. They're dynamic, evolving over time and space. They're the fingerprints of the universe, revealing the hidden order behind what might seem like chaos. And as we begin to decode these patterns, we might just uncover the keys to unlocking some of the universe's greatest mysteries. So, what if these threads of the cosmic tapestry hold the answers to questions we've barely begun to ask? Let's keep exploring to find out. To understand the origins of these universal patterns, we need to travel back in time, back to the very beginning of everything. Picture the Big Bang, the moment when the universe burst into existence, not as a single explosion, but as the unfolding of an immense cosmic canvas. In those first fleeting moments, the universe was a seething, chaotic soup of energy and particles, but within that chaos, something extraordinary was happening. The seeds of order were being sown, the initial conditions of the universe, its temperature, density, and the fundamental forces at play, were like the first brushstrokes on a blank canvas, setting the stage for the patterns we see today. One of the most crucial elements in this early universe was symmetry. Symmetry is more than just a pleasing aesthetic. It's a fundamental principle that governs the behavior of particles and forces. In the earliest moments, the universe was perfectly symmetrical, with all forces unified into one. But as the universe expanded and cooled, this symmetry began to break, much like ice cracking under pressure. Out of this breaking symmetry emerged the four fundamental forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. This cosmic shift didn't just create the forces that shape our reality, it also laid the groundwork for the patterns that would come to define the structure of space and time. But symmetry wasn't the only player in this cosmic drama. Chaos, too, played a pivotal role. In the early universe, chaotic fluctuations in energy and density created tiny ripples, imperfections that would later grow into the vast cosmic web of galaxies and clusters we see today. These ripples were like the first notes in a symphony, setting the rhythm for the universe's evolution. Over billions of years, gravity amplified these ripples, pulling matter together into stars, galaxies, and the intricate filaments of the cosmic web. What began as chaos became order, a delicate balance between randomness and structure. Yet, even as these patterns emerged, they were never static. The universe is a dynamic, ever-changing entity, and so are its patterns. They evolve, adapt, and interact in ways that continue to shape the cosmos. The galaxies we see today, with their spiraling arms and glowing clusters, are the result of billions of years of cosmic evolution, driven by the interplay of symmetry, chaos, and the fundamental forces. And as we peer deeper into the universe, we're reminded that these patterns are not just relics of the past. They are the living, breathing framework of reality itself. So, if these patterns are the language of the universe, what happens when we learn to read them? What secrets might they reveal about the nature of existence? As we continue this journey, we'll explore how these universal patterns aren't just a product of the past. They're the key to understanding the future. Symmetry is more than just a pleasing aesthetic. It's a fundamental principle that underpins the very fabric of the universe. From the tiniest particles to the grandest galaxies, symmetry acts as an invisible architect, shaping the patterns we see around us. But what exactly is symmetry in this cosmic context? It's not just about mirror images or perfectly balanced shapes. It's about the underlying order that governs how things behave. In physics, symmetry refers to the idea that certain properties or behaviors remain unchanged even when conditions shift. Rotational symmetry, for example, means that a system looks the same no matter how you turn it, while translational symmetry implies that the laws of physics don't change from one point in space to another. These symmetries are the silent rules that keep the universe running smoothly. Take a snowflake, for instance. Each flake is a masterpiece of hexagonal symmetry, its intricate pattern repeated perfectly across 6 identical branches. This isn't just a random quirk of nature, it's a direct result of the molecular structure of water and the way it crystallizes under specific conditions. The snowflake's symmetry is a tiny echo of the same principles that govern the cosmos on a much larger scale. Now look up at the night sky, and you'll see another stunning example: the spiral arms of galaxies. These vast, swirling structures are not random. They're the result of rotational symmetry acting over billions of years, as gravity and angular momentum shape stars and gas into these mesmerizing forms. But symmetry isn't just about creating order, it's also about transformation. One of the most fascinating aspects of symmetry is how it can break, giving rise to new structures and complexities. Think of it like a perfectly balanced spinning top. When it spins smoothly, it's symmetrical, but if it wobbles and falls, that symmetry breaks, creating new patterns of motion. In the early universe, symmetry-breaking events were crucial in shaping the cosmos. As the universe cooled and expanded, the perfect symmetry of the initial conditions began to crack, giving rise to the diverse forces and particles we see today. This process, known as spontaneous symmetry breaking, is what allowed the universe to evolve from a uniform, featureless state into the rich, varied tapestry we observe now. So, while symmetry provides the blueprint, it's the breaking of that symmetry that brings the universe to life. These moments of transformation are like cosmic turning points, where the balance shifts and new possibilities emerge. And as we continue to explore these patterns, we're reminded that the universe is not just a static collection of rules. It's a dynamic, ever-changing entity, full of surprises waiting to be uncovered. What other secrets might symmetry and its breaking hold? As we delve deeper, we'll see how these principles continue to shape the cosmos, from the smallest particles to the largest structures. Symmetry breaking is one of the most profound and transformative processes in the universe. It's the moment when order and chaos collide, giving rise to the rich diversity we see around us. Think of it like a perfectly balanced seesaw. When one side tips ever so slightly, the entire system shifts, creating a cascade of new possibilities. In the cosmos, symmetry breaking is what transforms uniformity into complexity, turning a featureless void into a vibrant, dynamic universe. Take the early universe as an example. In its infancy, everything was perfectly symmetrical. A single, unified force governed all interactions, but as the universe expanded and cooled, this symmetry began to fracture. It's like pouring water onto a smooth sheet of ice. At first, the surface is uniform, but as the temperature drops, cracks begin to form, creating intricate patterns. In the cosmos, this cracking of symmetry gave rise to the four fundamental forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. Each of these forces emerged as a distinct entity, shaping the universe in unique ways. Without this breaking of symmetry, the cosmos would have remained a bland, unchanging expanse, devoid of the structures and phenomena we observe. One of the most striking examples of symmetry breaking can be seen in the formation of galaxies. In the early universe, matter was distributed almost uniformly, but tiny fluctuations in density ripples left over from the Big Bang acted as seeds for future structures. As gravity began to pull matter together, these ripples grew, breaking the initial symmetry of the cosmos. Over billions of years, these asymmetrical clumps of matter evolved into the galaxies, stars, and planets we see today. Without this delicate interplay between symmetry and its breaking, the universe would lack the breathtaking diversity of celestial bodies that fill the night sky. But symmetry breaking isn't just a cosmic phenomenon, it's also at work on a much smaller scale. Consider the way water molecules arrange themselves into ice crystals. At high temperatures, water molecules move freely, their arrangement symmetrical and uniform. But as the temperature drops, the molecules begin to lock into place, forming the intricate, hexagonal patterns of a snowflake. This process, known as spontaneous symmetry breaking, is a microcosm of what happens on a grand scale in the universe. It's a reminder that the same principles govern both the smallest particles and the largest structures, creating a seamless connection between the micro and the macro. What's truly fascinating is how symmetry breaking introduces an element of unpredictability into the universe. While symmetry provides the rules, it's the breaking of those rules that allows for creativity and complexity. It's as if the universe is an artist, using symmetry as a framework but breaking it to create something entirely new and unexpected. This interplay between order and chaos is what gives the cosmos its richness, its beauty, and its endless capacity for surprise. And this is where chaos theory comes into play. While symmetry breaking sets the stage for diversity, chaos theory helps us understand how small changes can lead to vastly different outcomes. Together, these concepts reveal a universe that is both ordered and unpredictable, a place where the tiniest fluctuations can ripple out to shape the grandest structures. As we continue to explore these ideas, we'll see how the dance between symmetry and chaos defines not just the universe's past, but its future as well. Chaos theory might sound like a contradiction, when we're talking about the universe's intricate patterns, but it's actually one of the most fascinating ways to understand how order emerges from apparent randomness. At its core, chaos theory explores how tiny changes in initial conditions can lead to dramatically different outcomes, a concept often referred to as the butterfly effect. Picture this: a butterfly flapping its wings in one part of the world could, in theory, set off a chain of events that eventually leads to a hurricane on the other side of the globe. While this might seem like an exaggeration, it perfectly illustrates how small, seemingly insignificant actions can have far-reaching consequences. Now, imagine this principle on a cosmic scale. In the vast expanse of space, chaos theory plays a crucial role in shaping the universe. Take the formation of star systems, for example. When a massive cloud of gas and dust begins to collapse under its own gravity, the tiniest variations in density or temperature can determine whether it forms a single star, a binary system, or even an entire cluster of stars. These initial fluctuations might seem minor, but they set the stage for entirely different cosmic outcomes. In some cases, a slight shift in the distribution of matter could mean the difference between a stable planetary system and a chaotic, star-devouring black hole. It's a reminder that even in the seemingly predictable laws of physics, there's room for unpredictability and surprise. But chaos doesn't just apply to the birth of stars. It also influences the behavior of black holes, some of the most enigmatic objects in the universe. Black holes are often thought of as singularities, points of infinite density where the laws of physics as we know them break down, yet even these cosmic behemoths are subject to the principles of chaos. The way matter spirals into a black hole, forming an accretion disk, is incredibly sensitive to initial conditions. A slight change in the angle or speed of incoming matter can lead to wildly different patterns of radiation and energy release. This unpredictability makes black holes not just fascinating objects of study, but also windows into the chaotic nature of the cosmos. What's truly remarkable is that chaos theory doesn't negate the idea of universal patterns, it enhances it. While chaos might seem like the opposite of order, it's actually a mechanism through which complexity emerges. Think of it like a painter splashing colors onto a canvas. At first glance, the strokes might appear random, but over time, patterns begin to form, revealing a deeper structure beneath the surface. In the same way, chaos theory shows us that even in the most unpredictable systems, there's an underlying order waiting to be discovered. The universe isn't just a collection of static patterns, it's a dynamic, ever-evolving tapestry where chaos and order dance together in a delicate balance. So, what does this mean for our understanding of the cosmos? It suggests that the universe is far more interconnected than we might realize, with even the smallest events capable of shaping the grandest structures. And as we continue to explore these ideas, we'll see how the interplay between chaos and order isn't just a feature of the universe, it's the very essence of how it works. How might this dance between chaos and symmetry unfold in other cosmic phenomena? That's where our journey takes us next. Among the many universal patterns that shape our cosmos, few are as mesmerizing and profound as fractals. These intricate, self-similar designs repeat themselves across different scales, creating a sense of infinite complexity that feels almost otherworldly. Picture a tree, its branches splitting into smaller branches, which in turn split into even smaller twigs. Each part mirrors the whole, creating a pattern that feels both familiar and endlessly intricate. This self-similarity isn't just a quirk of nature, it's a fundamental feature of the universe, appearing everywhere from the microscopic to the cosmic. Fractals are more than just beautiful designs, they're a window into the very fabric of reality. Take, for instance, the way galaxies form. On a grand scale, the distribution of matter in the universe isn't random, it follows a fractal pattern. Clusters of galaxies are connected by vast filaments, creating a cosmic web that mirrors the branching patterns of a tree or the veins in a leaf. Zoom in closer, and you'll find the same fractal geometry in the way clouds form, rivers carve their paths, or even in the structure of our lungs. These patterns aren't coincidental. They're the result of universal laws that govern how matter organizes itself across scales. What makes fractals so fascinating is their infinite depth. No matter how much you zoom in or out, the pattern remains consistent, revealing new layers of complexity with each level of magnification. This property, known as self-similarity, suggests that the universe operates on a set of scaling rules that apply equally to the smallest particles and the largest structures. These scaling laws are like the hidden grammar of the cosmos, dictating how energy, matter, and information flow through the fabric of space and time. One of the most striking examples of fractals in action is the Mandelbrot set, a mathematical construct that reveals an endless cascade of intricate shapes and patterns. While it's a purely mathematical creation, the Mandelbrot set mirrors the kind of self-similarity we see in nature, from the jagged edges of coastlines to the swirling arms of galaxies. It's as if the universe has embedded these patterns into its very DNA, using them as a universal language to express its complexity. But fractals aren't just about beauty or symmetry. They also play a crucial role in understanding the universe's structure and behavior. For instance, fractal geometry helps scientists model phenomena like turbulence in fluids, the growth of plants, and even the way galaxies cluster together. By studying these patterns, we gain insights into the underlying principles that govern the cosmos, from the quantum realm to the vastness of space. As we explore the concept of fractals, we begin to see how scaling laws, the rules that dictate how patterns repeat across different sizes, play a pivotal role in shaping the universe. These laws are like the universal rhythms that ensure harmony across scales, from the tiniest subatomic particles to the largest superclusters of galaxies. And as we delve deeper into these ideas, we'll uncover how fractals and scaling laws are not just patterns, they're the threads that weave the universe together, creating a tapestry of infinite complexity and wonder. What other secrets might these patterns hold? Let's continue our journey to find out. Scaling laws are the hidden rules that govern how the universe behaves across different sizes, from the tiniest particles to the largest cosmic structures. These mathematical relationships show us that certain properties don't just change randomly as things grow or shrink. They follow precise patterns that repeat across scales. Imagine a tree growing taller. As it does, its branches, leaves, and roots all grow in proportion, following a set of rules that ensure stability and balance. In the same way, scaling laws reveal that the universe operates on a set of universal principles, creating harmony between the micro and the macro. One of the most striking examples of scaling laws can be found in the stars. Take the relationship between a star's mass and its luminosity, the amount of light it emits. It turns out that a star's brightness isn't just proportional to its size. It follows a precise mathematical relationship. A star twice as massive as another doesn't just shine twice as bright. It can shine up to 16 times brighter. This relationship, known as the mass-luminosity law, shows us that even in the vastness of space, there's a predictable order to how energy is produced and distributed. It's a reminder that the universe isn't just a random collection of objects, it's a finely tuned system, governed by laws that transcend size. But scaling laws don't just apply to stars, they also shape the large-scale structure of the cosmos. Consider the distribution of cosmic voids, the vast, empty regions between galaxies and galaxy clusters. These voids aren't randomly scattered, they follow a pattern that reflects the underlying structure of the universe. Just as the branches of a tree grow in proportion to its trunk, the size and distribution of these voids are governed by scaling laws that reveal the interconnectedness of cosmic matter. This intricate web of galaxies and voids, known as the cosmic web, is a testament to the universe's ability to organize itself according to universal principles. What's truly fascinating is how these scaling laws aren't limited to one type of phenomenon, they appear across different areas of physics and nature. Whether it's the way rivers branch, the way animals' metabolic rates change with body size, or the way galaxies cluster together, scaling laws show us that the universe operates on a set of shared rules. These rules create a sense of unity, linking the smallest particles to the largest structures in a seamless tapestry of order and complexity. And here's the intriguing part. These scaling laws aren't just mathematical curiosities, they're encoded in the very fabric of space-time. The way matter and energy interact, the way forces propagate, and the way structures form are all governed by these universal principles. They're like the invisible threads that weave the cosmos together, ensuring that patterns repeat and order emerges, no matter the scale. As we continue to explore these ideas, we'll see how scaling laws aren't just a feature of the universe, they're the foundation upon which it's built. What other secrets might these universal rules hold? That's where our journey takes us next. Now, let's turn our attention to the geometry of space-time itself, a concept that lies at the heart of how we understand the universe's patterns. Picture space-time as a vast, flexible fabric, not flat and rigid, but dynamic and malleable, capable of bending, stretching, and curving. This curvature isn't just an abstract idea, it's the very foundation of gravity and the force that shapes the motion of planets, stars, and even light. According to Einstein's theory of general relativity, massive objects like stars and planets don't just sit passively in space, they warp the fabric of space-time around them, creating ripples and curves that influence everything nearby. One of the most striking examples of this curvature is the way light behaves around massive objects. Imagine a beam of light traveling through space, passing near a massive star or galaxy. Instead of moving in a straight line, the light bends, following the curve of space-time created by the object's gravity. This phenomenon, known as gravitational lensing, isn't just a theoretical prediction. It's been observed countless times, from the bending of starlight around our own sun to the distorted images of distant galaxies seen through the lens of massive galaxy clusters. These observations are like cosmic fingerprints, revealing the hidden geometry of space-time and how it shapes the patterns we see in the universe. But curvature doesn't just affect light, it also dictates the motion of planets and stars. Take our own solar system as an example. The reason Earth orbits the Sun isn't because the Sun pulls on it in the traditional sense, but because the Sun's mass curves the space-time around it, creating a kind of cosmic well. Earth, like all planets, follows the contours of this curved space-time, tracing out an elliptical path. It's as if the planets are rolling along the surface of a giant, invisible funnel, their orbits shaped by the geometry of space-time itself. This elegant interplay between mass and curvature is what keeps the solar system, and indeed the entire universe, in motion. And then there are gravitational waves, the ripples in space-time caused by some of the most violent events in the cosmos, like colliding black holes or neutron stars. These waves are like the echoes of massive cosmic collisions, traveling across the universe and subtly stretching and squeezing space-time as they pass. Detecting gravitational waves was a monumental achievement, not just because it confirmed a key prediction of general relativity, but because it gave us a new way to listen to the universe. These waves carry information about the events that created them, offering insights into the geometry of space-time and the patterns that emerge from its curvature. Yet, as profound as general relativity is, it's not the whole story. While it beautifully explains the large-scale structure of the universe, there's another realm where the rules seem to change entirely: the quantum world. Here, the smooth, curved geometry of space-time gives way to a far more chaotic and uncertain landscape, where particles pop in and out of existence, and the fabric of reality seems to flicker like a static-filled TV screen. This is where quantum mechanics takes the stage, offering a radically different perspective on the patterns that shape the universe. So, as we marvel at the elegance of space-time's geometry, we're also reminded that the universe is full of surprises, with layers of complexity waiting to be uncovered. What happens when we combine the large-scale curvature of general relativity with the strange, unpredictable world of quantum mechanics? That's where our exploration takes us next. Now, let's venture into the quantum realm, a place where the rules of the universe take a dramatic turn, and the familiar patterns of space-time give way to something far stranger. While the large-scale cosmos follows the elegant curvature described by general relativity, the subatomic world operates under a completely different set of rules, governed by quantum mechanics. Here, particles defy our everyday expectations, behaving in ways that seem almost magical. This is the domain of superposition, entanglement, and quantum tunneling phenomena that challenge not just our intuition, but the very foundations of how we understand reality. Take superposition, for instance. In the quantum world, particles don't exist in a single, definite state like we're used to in our macroscopic world. Instead, they can exist in multiple states at once, like a coin spinning in midair, neither heads nor tails, but both simultaneously. This bizarre principle was famously demonstrated in the double-slit experiment, where particles like electrons or photons are fired at a barrier with two slits. Instead of passing through one slit or the other, as you might expect, they behave like waves, creating an interference pattern on the other side. But here's the kicker: when you try to observe which slit the particle goes through, it suddenly behaves like a single particle again, collapsing its wave like nature. It's as if the mere act of looking changes the behavior of the particle, a concept that still baffles scientists today. Then there's quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, their properties become linked, no matter how far apart they are. If you measure one particle, the other instantly knows and adjusts its state accordingly, even if it's on the other side of the universe. This instantaneous connection seems to defy the speed of light, challenging our classical understanding of space and time. It's as if the universe has a hidden network of connections that operates outside the bounds of what we can see or measure. And let's not forget quantum tunneling, another mind-bending phenomenon where particles can pass through barriers that should be impossible to cross. Imagine throwing a ball at a wall and watching it suddenly appear on the other side without breaking the wall. That's essentially what happens in the quantum world. Electrons, for example, can tunnel through energy barriers, a process that's crucial for the functioning of everything from stars to modern electronics. This ability to defy classical physics is what makes quantum mechanics so powerful and so perplexing. What's truly remarkable is how these quantum patterns don't just exist in isolation, they're woven into the fabric of reality itself. From the behavior of atoms in a molecule to the processes that power the sun, quantum mechanics underpins the workings of the universe at its most fundamental level. But here's the catch. While quantum mechanics excels at explaining the tiny, and general relativity dominates the large, the two theories don't play nicely together. Reconciling these two frameworks, uniting the quantum world with the geometry of space-time, remains one of the greatest challenges in modern physics. It's a puzzle that could unlock a deeper understanding of the universe, revealing patterns we've yet to imagine. As we explore these strange and wonderful phenomena, we're reminded that the universe is far more complex and far more mysterious than we often assume. What new patterns might emerge if we could finally bridge the gap between the quantum and the cosmic? That's a question that keeps physicists searching, and it's one that might just redefine our understanding of reality itself. The universe is a tapestry of patterns, but as we've seen, these patterns aren't all governed by the same rules. On one hand, we have the vast, curved geometry of space-time, where massive objects like stars and galaxies shape the cosmos through gravity. On the other, we have the bizarre, unpredictable world of quantum mechanics, where particles exist in multiple states at once and can teleport through barriers. These two frameworks, general relativity and quantum mechanics, are the cornerstones of modern physics, but they don't quite fit together. In fact, they seem to describe two entirely different universes. This is where the quest for a unified theory comes in, a grand framework that could bridge the gap between the quantum and the cosmic, revealing the deeper patterns that unite them. One of the most ambitious attempts at unification is string theory. Imagine if every particle in the universe wasn't a tiny dot, but a vibrating string, like a cosmic guitar string. These strings wouldn't just vibrate randomly, they'd resonate at specific frequencies, creating the different particles and forces we observe. String theory suggests that these tiny, vibrating strings are the building blocks of reality, weaving together the quantum and the cosmic into a single, elegant framework. It's a beautiful idea, but it comes with a catch. To make the math work, string theory requires extra dimensions, far more than the three spatial dimensions and one time dimension we're familiar with. While this might sound like science fiction, it's a serious attempt to reconcile the microscopic world of quantum mechanics with the large-scale structure of general relativity. Then there's loop quantum gravity, another leading candidate for a unified theory. Instead of strings, this theory proposes that space-time itself is made up of tiny, interconnected loops. Picture the fabric of space-time not as a smooth continuum, but as a network of loops, like a cosmic tapestry woven from threads. These loops would be incredibly small, far smaller than an atom, and they'd create a kind of quantum structure for space-time, bridging the gap between the quantum and the cosmic. Loop quantum gravity doesn't require extra dimensions, but it does challenge our understanding of space and time, suggesting that they might be quantized, broken into discrete, indivisible units. The holographic principle offers yet another perspective. It suggests that all the information in a volume of space can be thought of as encoded on its boundary, like a hologram. In this view, the three-dimensional universe we experience might be a projection of information stored on a two-dimensional surface. This idea draws from the behavior of black holes, where information about what falls into them seems to be encoded on their event horizons. The holographic principle hints at a profound connection between the microscopic and the macroscopic, suggesting that the patterns we see in the universe might be the result of deeper, more fundamental processes. Yet, despite the elegance of these theories, none have been proven. The challenge lies in testing them experimentally. The energy scales and distances involved are so extreme that they're far beyond anything we can currently measure. But there's hope. Some researchers believe that dark matter and dark energy, the mysterious substances that make up most of the universe, could hold clues to these universal patterns. Dark matter, which doesn't interact with light but exerts gravitational pull, and dark energy, which drives the accelerated expansion of the universe, might be the keys to unlocking a deeper understanding of how the quantum and the cosmic are connected. Could these enigmatic forces be the missing pieces of the puzzle? As we explore these questions, we're reminded that the universe is full of mysteries waiting to be solved, and that the search for a unified theory is far from over. Let's shift our gaze to one of the most elusive and mysterious components of the universe, dark matter. Unlike the stars, planets, and galaxies we can see, dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, despite its invisibility, its presence is undeniable. Dark matter is the unseen architect of the cosmos, its gravitational pull shaping the large-scale structure of the universe in ways that are both profound and perplexing. Without it, the universe as we know it simply wouldn't exist. To understand dark matter's role, let's look at the cosmic web, the vast, intricate network of galaxies and galaxy clusters that stretches across the universe. This web isn't random, it's a carefully woven tapestry, and dark matter is the loom on which it's built. When the universe was young, dark matter began to clump together under the influence of gravity, forming dense regions that acted like cosmic scaffolding. Ordinary matter, the stuff that makes up stars, planets, and us, was drawn to these clumps, eventually collapsing into the galaxies and clusters we see today. In this way, dark matter provided the blueprint for the universe's structure, guiding the formation of everything from the smallest galaxies to the largest superclusters. But how do we know dark matter exists if we can't see it? The answer lies in its gravitational effects. Take galaxy rotation curves, for example. When astronomers measure how fast stars orbit the centers of galaxies, they find something surprising. The outer stars move much faster than they should based on the visible matter alone. This discrepancy suggests that there's an invisible source of gravity, dark matter, holding these galaxies together. Similarly, observations of galaxy clusters reveal that their gravitational pull is far stronger than what the visible matter can account for, further evidence of dark matter's pervasive influence. Despite its critical role, dark matter remains one of the greatest mysteries in modern physics. We know it exists because of its gravitational effects, but we have no idea what it's made of. Is it a new type of particle, one that interacts so weakly with ordinary matter that it's nearly impossible to detect? Or could it be something even more exotic, like tiny primordial black holes? Scientists have been searching for answers for decades, using everything from underground detectors to powerful particle colliders, but so far, dark matter has managed to elude us. Its nature is still a puzzle, one that could hold the key to understanding the universe on a deeper level. What's fascinating is that dark matter doesn't act alone. It works in tandem with another mysterious force, dark energy. While dark matter pulls the universe together, creating structure, dark energy pushes it apart, driving the accelerated expansion of the cosmos. Together, These two invisible forces shape the universe in ways we're only beginning to comprehend. Dark energy might seem like the opposite of dark matter, but in reality, they're complementary, each playing a crucial role in the cosmic dance of creation and expansion. As we continue to explore the mysteries of dark matter, we're reminded that the universe is full of surprises, with hidden forces and patterns waiting to be uncovered. What other secrets might this invisible architect hold, and how does its interplay with dark energy shape the destiny of the cosmos? These are questions that drive scientists to keep searching, pushing the boundaries of our understanding. And as we delve deeper, we'll see how these unseen forces are not just shaping the universe, they're reshaping our very understanding of reality itself. If dark matter is the unseen architect shaping the universe, then dark energy is the invisible force pushing it apart. This mysterious entity, which makes up about 68% of the cosmos, is responsible for the accelerated expansion of the universe, a discovery that turned our understanding of space-time on its head. Unlike gravity, which pulls matter together, dark energy acts as a kind of cosmic repulsion, stretching the fabric of space-time itself. It's as if the universe is being pulled apart from the inside, with galaxies racing away from each other faster and faster as time goes on. But what exactly is dark energy, and why does it behave in such a counterintuitive way? The story of dark energy begins with one of the most surprising discoveries in modern astronomy. In the late 1990s, scientists studying distant supernova exploding stars expected to find that the expansion of the universe was slowing down due to gravity's pull. Instead, they discovered the opposite. The universe was expanding at an accelerating rate. This revelation was so shocking that it earned the researchers a Nobel Prize and permanently altered our understanding of the cosmos. The only way to explain this acceleration was to propose the existence of a new, unknown force, dark energy. One of the leading theories about dark energy is that it's tied to the very fabric of space-time itself. According to this idea, empty space isn't truly empty, it's filled with a kind of energy that permeates the entire universe. This energy, sometimes called the cosmological constant, acts like a counterforce to gravity, pushing galaxies apart as space itself expands. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, the dots move away from each other, not because they're moving through space, but because the space between them is stretching. In the same way, dark energy is causing the universe to stretch, creating ever larger gaps between galaxies. But this raises an intriguing question. What does the future hold for a universe dominated by dark energy? If the expansion continues to accelerate, galaxies will eventually move so far apart that they'll be isolated from one another, lost in an ever-expanding void. Over trillions of years, the night sky would grow darker and darker as distant galaxies fade from view, leaving only the local group of galaxies bound together by gravity. It's a cosmic destiny that feels both awe-inspiring and deeply unsettling, a reminder of the profound forces at work in the universe. Dark energy doesn't just shape the future of the cosmos, it also influences its structure on a grand scale. While dark matter creates the scaffolding for galaxies and clusters, dark energy determines how those structures evolve over time. For instance, as the universe expands, the gravitational pull of dark matter becomes weaker relative to the repulsive force of dark energy. This delicate balance between attraction and repulsion is what shapes the large-scale patterns we observe, from the distribution of galaxies to the cosmic voids that stretch between them. Yet, as much as dark energy explains, it also challenges our understanding of space-time. Why does it exist? Why does it have the strength it does? These questions remain unanswered, leaving scientists to grapple with the possibility that dark energy might be more than just a force. It could be a fundamental property of the universe itself, woven into the very fabric of reality. And here's where black holes come into play. These enigmatic objects, with their immense gravitational pull, might hold clues to the nature of dark energy and the patterns that govern the cosmos. By studying the way black holes interact with space-time, we might uncover new insights into the forces that shape our universe. What secrets might black holes reveal about the interplay between gravity, dark energy, and the geometry of space-time? That's where our journey takes us next, into the heart of one of the universe's most mysterious phenomena. Black holes are among the most extreme and enigmatic phenomena in the universe, where the fabric of space-time is stretched and warped to its absolute limits. These cosmic behemoths are not just massive objects, they are extreme manifestations of universal patterns, bending the rules of physics in ways that challenge our understanding of reality. At the heart of a black hole lies the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. It's as if space-time itself folds inward, creating a one-way door to a realm where gravity reigns supreme. But black holes aren't just destructive forces, they're also incredible laboratories for testing the limits of our theories. Take Hawking radiation, for example. Named after the legendary physicist Stephen Hawking, this phenomenon suggests that black holes aren't entirely black. Due to quantum effects at the event horizon, black holes can emit tiny amounts of radiation, slowly losing mass over time. This discovery was groundbreaking because it bridged the worlds of quantum mechanics and general relativity, two frameworks that rarely intersect. Hawking radiation shows that even in the most extreme environments, the universe finds a way to balance order and chaos, offering glimpses into the deeper patterns that govern existence. One of the most fascinating aspects of black holes is their ability to warp space-time so profoundly that they create gravitational lenses. When light from a distant object passes near a black hole, it bends around the intense gravitational field, creating distorted or magnified images of the background object. This effect isn't just a tool for astronomers to study distant galaxies, it's also a vivid demonstration of how space-time behaves under extreme conditions. By observing these distortions, scientists can test predictions made by Einstein's theory of general relativity, confirming that even in the most extreme environments, the geometry of space-time follows the patterns laid out by his equations. And then there's the concept of time dilation near a black hole. As you approach the event horizon, time slows down relative to an outside observer. To someone watching from a distance, it might seem like you're frozen in time, forever hovering at the edge of the black hole. For you, however, time would feel normal, even as you're pulled inexorably toward the singularity. This bizarre effect isn't just a thought experiment, it's a real consequence of the way gravity warps space-time, offering a tangible example of how the universe's patterns play out on the grandest scales. But black holes don't just distort space-time, they also create ripples in it. When two black holes collide, they send out gravitational waves, ripples in the fabric of space-time that travel across the universe at the speed of light. These waves are like cosmic echoes, carrying information about the cataclysmic events that created them. The detection of gravitational waves in 2015 was a monumental achievement, not just because it confirmed a key prediction of general relativity, but because it gave us a new way to listen to the universe. These ripples are more than just signals, they are a window into the hidden patterns of space-time, revealing how even the most violent events in the cosmos follow universal rhythms. As we explore these cosmic phenomena, we're reminded that black holes are more than just mysterious objects, they're gateways to understanding the deeper patterns that shape the universe. From the way they warp space-time to the ripples they send across the cosmos, black holes offer a unique perspective on the interplay between gravity, quantum mechanics, and the geometry of existence. And as we continue to study these cosmic enigmas, we might just uncover the secrets that tie the quantum world to the vastness of space-time itself. So, what happens when these ripples reach us? That's where our journey takes us next, into the world of gravitational waves and the stories they tell about the universe's most dramatic events. Gravitational waves are the universe's way of whispering its secrets to us, rippling through the fabric of space-time like echoes of cosmic events that defy imagination. These waves are not just theoretical constructs, they are real, measurable phenomena, born from some of the most violent and energetic events in the cosmos. Imagine two black holes, each billions of times more massive than our Sun, spiraling toward each other in a deadly dance. As they collide, they release an immense burst of energy, sending shockwaves through space-time itself. These ripples are gravitational waves, and they carry with them the story of the universe's most dramatic moments. The first direct detection of gravitational waves in 2015 was a watershed moment in astrophysics, marking the dawn of a new era in our ability to observe the cosmos. The event, known as GW 150914, was caused by the merger of two black holes over 1 billion light-years away. When the waves reached Earth, they were detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a pair of exquisitely sensitive instruments designed to measure the tiniest distortions in space-time. The detection confirmed a century-old prediction made by Albert Einstein and opened up an entirely new way of studying the universe, one that doesn't rely on light, but on the vibrations of space-time itself. What makes gravitational waves so extraordinary is their ability to reveal the hidden patterns of the universe in ways light never could. Unlike electromagnetic waves, which can be absorbed, scattered, or blocked by cosmic dust, gravitational waves travel unimpeded through the cosmos, carrying information about their origins directly to us. This means we can listen to events that are otherwise invisible, like black hole mergers, neutron star collisions, or even the faint echoes of the Big Bang itself. It's as if the universe has handed us a new set of ears, allowing us to hear the cosmic symphony in all its complexity. The implications of this discovery are profound. Gravitational waves not only confirm the existence of black holes and other exotic objects, but they also provide a new tool for testing the limits of our understanding of space-time. For example, the waves from black hole mergers allow us to probe the nature of gravity in extreme environments, offering insights into how space-time behaves under conditions that would be impossible to replicate on Earth. Each wave is like a cosmic fingerprint, encoding details about the objects that created it, their masses, spins, and even the shape of their orbits before they collided. But perhaps the most tantalizing possibility is what gravitational waves might tell us about the early universe. In the moments after the Big Bang, the cosmos was a seething cauldron of energy and matter, filled with fluctuations that would later grow into galaxies and clusters. Some of these fluctuations may have produced gravitational waves, ripples that have been traveling through the universe ever since. If we can detect these primordial waves, they could offer a glimpse into the universe's infancy, revealing patterns that have shaped everything we see today. As we continue to refine our ability to detect and interpret gravitational waves, we're reminded that the universe is full of stories waiting to be heard. These ripples in space-time are more than just cosmic curiosities. They're the threads that connect us to the most distant and mysterious corners of existence. And as we listen to their whispers, we might just uncover the deeper rhythms that bind the cosmos together. What other secrets might these waves hold? That's where our journey takes us next, into the echoes of the early universe and the patterns that shaped everything we know. The cosmic microwave background, or CMB, is like a cosmic time capsule, a faint glow of light that has been traveling through the universe for over 13 billion years, carrying with it the story of the universe's earliest moments. This ancient light is the afterglow of the Big Bang, a snapshot of the universe when it was just a hot, dense soup of particles and energy. Today, the CMB fills the entire cosmos, a nearly uniform sea of microwaves that permeates every corner of space. But hidden within this faint glow are tiny variations, fluctuations so small they might seem insignificant, yet they hold the key to understanding how the universe evolved into the intricate web of galaxies and clusters we see today. These fluctuations in the CMB are like the cosmic equivalent of fingerprints, unique patterns that reveal the conditions of the universe just 380,000 years after the Big Bang. At this point, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. The photons released during this era have been traveling ever since, gradually stretching into microwaves as the universe expanded. When we map the CMB, we're essentially looking at a baby picture of the universe, capturing the moment it transitioned from a hot, opaque plasma to a transparent, cooling expanse. But what do these tiny fluctuations mean? They're the seeds of structure in the universe, the initial ripples that would grow over billions of years into the galaxies, stars, and planets we see today. Imagine tossing a handful of pebbles into a still pond. The ripples spread out, eventually creating a complex pattern of waves. In the same way, the fluctuations in the CMB were the first ripples in the fabric of the universe, small variations in density and temperature that gravity would later amplify into the vast cosmic web. These patterns aren't random. They follow precise mathematical relationships, reflecting the fundamental laws that govern the early universe. One of the most remarkable things about the CMB is how uniform it is. The temperature of the cosmic microwave background is almost exactly the same in every direction, varying by less than 1 part in 100,000. This uniformity suggests that the early universe was incredibly homogeneous, a smooth expanse of matter and energy with only the tiniest imperfections. But those imperfections are crucial. They are the blueprint for the structures we see today. Without them, the universe would have remained a featureless void, lacking the complexity and diversity that make it so fascinating. So, how did these fluctuations arise? That's where inflation theory comes into play. According to this idea, the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. During this rapid expansion, quantum fluctuations, tiny, random variations in energy, were stretched to cosmic scales, creating the seeds of structure we see in the CMB. Inflation not only explains the uniformity of the CMB, but also provides a framework for understanding how those tiny ripples grew into the vast cosmic structures we observe today. It's as if the universe used quantum mechanics as a paintbrush, creating the first strokes of a masterpiece that would take billions of years to complete. As we study the CMB, we're reminded that the universe's patterns are not just beautiful, they are deeply rooted in the physics of its earliest moments. From the tiniest fluctuations to the largest structures, the cosmos is a tapestry woven from the threads of its own history. And as we continue to explore these echoes of the Big Bang, we're uncovering the story of how the universe grew from a hot, dense beginning into the rich, dynamic expanse we call home. What other secrets might the CMB hold? That's where our journey takes us next, into the mysteries of inflation and the forces that shaped the universe's infancy. Inflation theory is one of the most compelling ideas in modern cosmology, offering a bold explanation for how the universe evolved from a hot, dense state into the vast, structured cosmos we see today. To grasp its significance, let's rewind to the universe's earliest moments, just a fraction of a second after the Big Bang. At this point, the cosmos was unimaginably small and hot, filled with a seething sea of energy. But then, something extraordinary happened, a brief but explosive period of exponential expansion known as inflation. In less than a blink of an eye, the universe expanded faster than the speed of light, stretching from a size smaller than an atom to something far larger than our observable universe today. This rapid expansion wasn't just a dramatic event, it was the cosmic equivalent of hitting the reset button, smoothing out irregularities and setting the stage for the patterns we observe in the universe. One of the most striking consequences of inflation is the uniformity of the cosmic microwave background, the faint glow of light left over from the Big Bang. Without inflation, it's hard to explain why the CMB looks so similar in every direction, even in regions that were too far apart to have ever been in contact. Inflation solves this puzzle by stretching the universe so rapidly that previously connected regions were pulled apart, leaving behind a nearly uniform background. But inflation didn't just create uniformity, it also planted the seeds for future structure. Tiny quantum fluctuations, random variations in energy, were stretched to cosmic scales during this rapid expansion. These fluctuations became the blueprint for galaxies, galaxy clusters, and the cosmic web, the intricate network of matter that defines the large-scale structure of the universe. Another key piece of evidence supporting inflation is the flatness of the universe. Imagine the universe as a sheet of paper. If it were curved, like the surface of a sphere or a saddle, the geometry of space-time would behave differently. But observations of the CMB and the distribution of galaxies suggest that the universe is remarkably flat, with a geometry that aligns perfectly with the predictions of inflation. This flatness is a direct consequence of the rapid expansion, which stretched space-time so dramatically that any initial curvature was smoothed out, much like blowing up a balloon flattens its surface. Yet, as elegant as inflation theory is, it raises profound questions about the nature of the universe. If inflation occurred once, could it have happened elsewhere, giving rise to other universes? This idea, known as the Multiverse Theory, suggests that our universe might be just one of countless others, each with its own unique set of physical laws and constants. While the multiverse remains speculative, it offers a tantalizing possibility that the patterns we observe in our universe might be part of a much larger, more complex tapestry, one that stretches far beyond the limits of our observable cosmos. As we continue to explore the implications of inflation, we're reminded that the universe is full of surprises, with layers of complexity waiting to be uncovered. What other mysteries might this theory hold, and how might it shape our understanding of the cosmos on the grandest scales? These are questions that keep scientists searching, pushing the boundaries of our knowledge. And as we delve deeper, we'll see how inflation isn't just a theory about the past. It's a key to understanding the future of the universe itself. What if our universe is just one thread in an infinite cosmic tapestry? This is the idea at the heart of the multiverse, a theory that suggests our universe is only one of countless others, each with its own unique set of patterns, laws, and even realities. Imagine a cosmic library where every book represents a different universe, each with its own story, rules, and structure. In some, the laws of physics might be slightly tweaked, gravity could be stronger, light might travel faster, or time itself could flow differently. In others, the fundamental constants that govern reality might be so alien that life as we know it could never exist. This isn't science fiction, it's a serious scientific hypothesis, one that challenges everything we think we know about space, time, and existence itself. One of the leading theories supporting the multiverse idea is eternal inflation. Picture the early universe as a bubbling pot of water, with each bubble representing a separate universe. As space expands, new bubbles form, each one a self-contained cosmos with its own unique properties. In this view, the Big Bang wasn't a one-time event. It was just one bubble popping into existence in an endless sea of universes. This theory not only explains the vastness of our own universe, but also suggests that there could be an infinite number of others, each with its own distinct patterns and possibilities. It's a staggering thought, one that stretches the imagination and redefines our place in the cosmos. Another fascinating angle comes from string theory, which proposes that the fundamental building blocks of reality are tiny, vibrating strings. These strings can exist in countless configurations, each one corresponding to a different universe with its own set of physical laws. This landscape of possibilities is vast, with an almost infinite number of potential universes. Some might have dimensions beyond the three spatial ones we're familiar with, while others could have entirely different forces governing their behavior. String theory's multiverse isn't just a collection of universes, it's a cosmic symphony, with each universe playing its own unique note in the grand composition of reality. But here's where things get even more intriguing. If the multiverse exists, it challenges our understanding of space-time in profound ways. In our universe, space-time is a four-dimensional fabric, but in others, it could be entirely different. Some universes might have more dimensions, while others might have fewer. Time itself could flow in multiple directions or behave in ways that defy our intuition. The multiverse idea forces us to rethink not just the nature of reality, but also the very framework we use to understand it. It's as if we've been handed a new set of tools, allowing us to explore possibilities that were once thought to be purely theoretical. And then there's the question of consciousness. If the multiverse exists, how do we perceive it? Some theories suggest that consciousness itself might play a role in shaping or interpreting these patterns. Imagine that our minds aren't just passive observers of reality, but active participants, tuning into the specific patterns of our universe while others remain hidden. This idea, sometimes called the participatory universe hypothesis, blurs the line between observer and observed, suggesting that our awareness might be intricately linked to the structure of reality itself. It's a mind-bending concept, one that raises more questions than it answers, but that's the beauty of the multiverse idea. It invites us to explore, to question, and to dream. As we ponder the possibilities of the multiverse, we're reminded that the universe, or universes, are far more mysterious and complex than we often assume. What other patterns might exist beyond the boundaries of our own reality, and how might these ideas reshape our understanding of existence? These are questions that push the limits of science and imagination, inviting us to look beyond the familiar and explore the infinite possibilities of the cosmos. And as we continue this journey, we'll see how the multiverse isn't just a theory, it's a gateway to understanding the deepest mysteries of reality itself. What if the patterns we see in the universe aren't just out there? What if they're shaped in some profound way by the very act of observing them? This idea might sound like something out of a science fiction novel, but it's a question that sits at the heart of both quantum mechanics and philosophy. It's called the observer effect, and it suggests that consciousness, our ability to observe and measure, plays a crucial role in how reality unfolds. At the quantum level, particles don't behave like solid objects with fixed properties. Instead, they exist in a kind of haze of possibilities, only settling into definite states when we observe them. It's as if the universe is waiting for us to look before deciding what's real. Take the famous double-slit experiment as an example. When particles like electrons or photons are fired at a barrier with two slits, they don't behave as expected. If no one is watching, they act like waves, creating an interference pattern on the other side. But the moment we try to measure which slit they pass through, they suddenly behave like particles, collapsing their wave like nature. This bizarre behavior has puzzled physicists for decades, raising questions about the role of the observer in shaping reality. Is it possible that consciousness itself is somehow intertwined with the fabric of the universe, influencing the patterns we perceive? This idea doesn't just challenge our understanding of physics, it also opens up deep philosophical questions about the nature of reality. If patterns only solidify when observed, do they exist independently of us? Or are they, in some sense, co-created by the act of observation? Some thinkers argue that reality is fundamentally relational, shaped by the interactions between observers and the observed. In this view, the universe isn't a static collection of objects waiting to be discovered. It's a dynamic, ever-changing interplay of relationships where patterns emerge through the act of engagement. But here's where things get even more intriguing. If consciousness plays a role in shaping reality, could it also influence the larger patterns we see in the cosmos? For instance, the way galaxies form or the way black holes behave might seem independent of human observation, but could there be a deeper connection between the micro and the macro? Some theories, like the participatory universe hypothesis, suggest that consciousness isn't just a passive observer, it's an active participant, shaping the very structure of reality. It's a radical idea, one that blurs the line between the observer and the observed, inviting us to rethink our place in the universe. As we explore these ideas, we're reminded that the patterns we see around us, whether in the quantum realm or the cosmic web, are not just external phenomena. They're deeply intertwined with how we perceive and interact with the world, and this brings us to another fascinating question. If consciousness shapes reality, what role does mathematics play in this dance? Mathematics is often described as the language of the universe, a tool we use to decode its patterns. But could it be more than that? Could mathematics itself be a kind of bridge between the observer and the observed, a way for us to connect with the deeper rhythms of existence? This interplay between consciousness, observation, and mathematics hints at a profound truth. The universe is not just a collection of patterns, it's a living, evolving conversation, one that we're all a part of. And as we continue to explore these questions, we'll see how the act of observing isn't just about seeing the world, it's about shaping it in ways we're only beginning to understand. So, what happens when we turn our attention to the language of these patterns? That's where our journey takes us next, into the elegant world of mathematics and its role in deciphering the cosmos. Mathematics has often been called the language of the universe, and for good reason. It's the tool we use to decode the intricate patterns woven into the fabric of reality, from the spirals of galaxies to the branching of trees. At its core, mathematics isn't just a human invention, it's a discovery, a way of uncovering the hidden rhythms and relationships that govern everything around us. Whether it's a simple equation or a complex theory, mathematics gives us a way to describe the world with precision and elegance, revealing the underlying order beneath the chaos. Take fractals, for example. These infinitely complex patterns, which repeat themselves at every scale, are a perfect illustration of how mathematics mirrors the natural world. The branching of a tree, the jagged edge of a coastline, or the swirling arms of a galaxy, all of these can be described using fractal geometry. The Mandelbrot set, a mathematical construct, is a stunning example of this. Its intricate, self-similar shapes are generated by a simple equation, yet they echo the complexity we see in nature. Fractals remind us that even the most chaotic systems often follow precise mathematical rules, creating beauty out of simplicity. Symmetry is another powerful concept that mathematics uses to describe the universe. From the hexagonal symmetry of a snowflake to the rotational symmetry of a galaxy, these patterns are everywhere. But symmetry isn't just about aesthetics, it's a fundamental principle that governs the behavior of particles and forces. In physics, symmetry groups help us understand how particles interact and how forces propagate through space-time. The standard model of particle physics, for instance, relies heavily on the concept of symmetry to explain the behavior of subatomic particles. It's as if the universe itself is a grand puzzle, and symmetry is one of the key pieces that helps us solve it. Differential equations are yet another example of how mathematics describes the patterns of the cosmos. These equations, which describe how quantities change over time, are essential for modeling everything from the motion of planets to the flow of fluids. When we calculate the trajectory of a comet or predict the weather, we're using differential equations to understand how systems evolve. They're like the mathematical equivalent of a time machine, allowing us to peer into the past and future of the universe's patterns. One of the most fascinating examples of mathematics in nature is the Fibonacci sequence. This series of numbers, where each number is the sum of the two preceding ones, appears in everything from the arrangement of leaves on a stem to the spirals of a sunflower. The sequence is a perfect example of how simple mathematical rules can give rise to complex and beautiful patterns. It's a reminder that the universe often follows elegant, predictable rules, even when the results seem endlessly varied. But mathematics doesn't just describe the universe, it also helps us visualize it. With modern technology, we can now create stunning visualizations of mathematical concepts, from 3D models of fractals to simulations of black holes. These tools allow us to see the patterns of the universe in ways that were once impossible, bringing abstract ideas to life. Imagine being able to watch a black hole warp space-time in real time, or see the intricate structure of a fractal unfold before your eyes. Technology has given us a new way to explore the mathematical beauty of the cosmos, making the invisible visible. As we continue to explore the language of mathematics, we're reminded that the universe is not just a collection of random events. It's a finely tuned system, governed by rules that we're only beginning to understand. And with each equation we solve, each pattern we uncover, we come a little closer to deciphering the grand design of existence. What other secrets might mathematics hold about the patterns of the cosmos? That's where our journey takes us next, into the tools and technologies that allow us to see these patterns in action. From the invisible ripples of gravitational waves to the vast cosmic web of galaxies, technology has become our window into the hidden patterns of the universe. Without it, we'd be left staring at the night sky, wondering but never knowing. Telescopes, for instance, have evolved far beyond the simple lenses Galileo used centuries ago. Today, instruments like the Hubble Space Telescope and the James Webb Space Telescope peer deep into the cosmos, capturing light from billions of years ago. These images aren't just breathtaking, they're data-rich snapshots that reveal the intricate structures of galaxies, the birth of stars, and even the faint glow of the cosmic microwave background. It's like having a time machine that lets us witness the universe's history unfold before our eyes. But it's not just about seeing farther, it's about seeing differently. Gravitational wave detectors, such as LIGO and Virgo, have opened up an entirely new way of observing the cosmos. These instruments don't rely on light, they listen to the vibrations of space-time itself, picking up the faint echoes of black hole collisions and neutron star mergers. When two black holes spiral into each other, they send ripples through the fabric of space-time, and these ripples can travel billions of light years to reach us. The first detection of gravitational waves in 2015 was a game changer, proving that we could hear the universe in ways we never thought possible. Each detection adds a new layer to our understanding, revealing the hidden choreography of massive objects dancing through space-time. Supercomputers, too, play a crucial role in decoding the universe's patterns. Imagine trying to simulate the formation of a galaxy or the collision of two neutron stars with pen and paper. It's simply impossible, but with the power of modern supercomputers, scientists can create detailed models of these events, running simulations that mimic the physics of the cosmos with astonishing accuracy. These simulations don't just recreate what we've observed, they predict what we might find next, guiding astronomers to new discoveries. For example, simulations of dark matter's behavior have helped us map the cosmic web, the vast network of galaxies and voids that stretches across the universe. It's like having a cosmic laboratory where we can test theories and explore possibilities that would otherwise be beyond our reach. And then there's the role of data. The amount of information collected by telescopes, detectors, and satellites is staggering, and making sense of it all requires cutting-edge technology. Machine learning algorithms, for instance, are now being used to sift through vast datasets, identifying patterns that might be missed by the human eye. These tools are helping us uncover subtle connections, from the way galaxies cluster together to the faint signals of distant exoplanets. It's a reminder that the universe's patterns aren't just out there, they're waiting to be discovered, decoded, and understood. But technology doesn't just help us observe and model the universe. It also allows us to visualize its beauty in ways that inspire wonder. Think of the stunning images of nebulae, the swirling arms of galaxies, or the intricate structure of a black hole's accretion disk. These visuals aren't just scientific tools, they're works of art that connect us to the cosmos on a deeply emotional level. And this brings us to an intriguing idea. If technology helps us see the universe's patterns, could art and culture be the way we interpret and celebrate them? From ancient cave paintings to modern digital art, humans have always sought to capture the rhythms and harmonies of the world around them. Perhaps in their own way, artists and storytellers have been mapping the patterns of existence long before we had telescopes or supercomputers. What might this intersection of science and creativity reveal about our place in the cosmos? That's where our journey takes us next. For centuries, humans have looked to the skies and the natural world, finding inspiration in the patterns that surround us. These universal rhythms, whether in the spirals of galaxies, the symmetry of snowflakes, or the branching of trees, have not only shaped our understanding of the cosmos, but have also deeply influenced our art, architecture, and cultural expressions. From the intricate designs of sacred geometry to the mesmerizing symmetry of mandalas, the patterns of the universe are woven into the very fabric of human creativity and spirituality. It's as if the cosmos has been whispering its secrets to us through the language of beauty and form, and we've been listening all along. Take sacred geometry, for instance. This ancient practice sees geometric shapes and patterns as reflections of divine order, a way to connect the physical world with the spiritual. The circle, for example, represents unity and infinity, while the triangle often symbolizes balance and harmony. These shapes aren't just abstract concepts, they're found everywhere, from the petals of a flower to the orbits of planets. In architecture, sacred geometry has been used to create spaces that feel harmonious and uplifting, like the domes of mosques or the stained glass windows of cathedrals. These structures aren't just buildings, they're expressions of a deeper connection to the patterns that govern existence. Then there's the golden ratio, a mathematical relationship that appears throughout nature and art. This ratio, approximately 1.618 to 1, is found in everything from the spirals of seashells to the proportions of the human body. Artists like Leonardo da Vinci and architects like Le Corbusier have used the golden ratio to create works that feel balanced and aesthetically pleasing. The Parthenon in Athens, for example, is often cited as a masterpiece of golden ratio design, its proportions echoing the patterns found in the natural world. It's a reminder that the same principles that shape the cosmos also resonate with our sense of beauty and harmony. Mandalas, too, are a powerful example of how universal patterns inspire human creativity. These circular designs, often used in spiritual practices, represent the cosmos and the interconnectedness of all things. In Hinduism and Buddhism, mandalas are used as tools for meditation, helping practitioners focus their minds and connect with the deeper rhythms of existence. The intricate symmetry of a mandala mirrors the patterns we see in nature, from the concentric rings of tree trunks to the spirals of galaxies. It's as if these designs are a bridge between the physical and the spiritual, a way for us to touch the infinite through art. But why do these patterns resonate so deeply with us? Perhaps it's because they reflect something fundamental about the universe and about ourselves. When we create art or design spaces that echo these patterns, we're not just imitating nature, we're tapping into a deeper sense of order and meaning. These patterns remind us that we're part of something larger, a cosmic tapestry that connects everything from the smallest atom to the largest galaxy. They speak to a universal language, one that transcends cultures and time. This connection between art, culture, and universal patterns isn't a modern discovery. It's something ancient civilizations understood intuitively. From the pyramids of Egypt to the stone circles of Stonehenge, these structures were often aligned with celestial events, reflecting a deep awareness of the cosmos's rhythms. The Mayans, for example, built their temples to align with the movements of the sun and stars, creating a living calendar that connected their daily lives to the patterns of the heavens. These ancient cultures didn't just observe the universe, they lived in harmony with it, using art and architecture to express their understanding of its deeper order. As we explore these connections, we're reminded that the patterns of the universe aren't just out there, they're within us, shaping our creativity, our spirituality, and our sense of wonder. And as we continue this journey, we'll see how these patterns have not only inspired human culture, but also guided our exploration of the cosmos itself. What other secrets might these ancient connections hold? That's where our exploration takes us next, into the ways humanity has used these patterns to navigate the mysteries of existence. Long before telescopes and supercomputers, ancient civilizations gazed at the stars and saw more than just points of light. They saw patterns. These early observers, from the Greeks to the Mayans, didn't have the tools we have today, but they had something just as powerful: curiosity and a deep connection to the natural world. Through careful observation and profound intuition, they began to uncover the rhythms of the cosmos, laying the groundwork for the science we practice today. Their insights into universal patterns, encoded in myths, monuments, and mathematical systems, reveal a timeless quest to understand the universe and our place within it. The Greeks, for instance, were masters of both philosophy and mathematics. Thinkers like Pythagoras and Plato saw the universe as a realm of perfect order, governed by mathematical principles. Pythagoras believed that numbers were the essence of all things, and his famous theorem is still a cornerstone of geometry today. Plato, on the other hand, imagined the cosmos as a series of nested spheres, each moving in perfect harmony, a concept that surprisingly aligns with our modern understanding of planetary orbits. Even the word cosmos, derived from the Greek word for order, reflects their belief in a structured, intelligible universe. These early ideas weren't just abstract musings, they were the seeds of scientific inquiry, planted in the fertile soil of human curiosity. Meanwhile, on the other side of the world, the Mayans were creating some of the most advanced astronomical systems of their time. Their meticulous observations of the night sky allowed them to predict celestial events with remarkable accuracy. The Mayan calendar, often misunderstood as a doomsday prophecy, was actually a complex system that tracked the cycles of the sun, moon, and planets. It's a testament to their ability to see patterns in the chaos of the cosmos. Their pyramids, aligned with the movements of celestial bodies, weren't just architectural marvels, they were cosmic clocks, connecting their daily lives to the rhythms of the heavens. These structures serve as a reminder that the universe's patterns aren't just something to observe, they're something to live by. But it wasn't just the Greeks and the Mayans who saw the universe as a tapestry of patterns. In ancient India, astronomers like Aryabhata made groundbreaking discoveries about the Earth's rotation and the nature of eclipses, while Chinese scholars meticulously recorded the movements of comets and stars, creating some of the earliest star maps. These cultures didn't just look at the sky, they engaged with it, using their observations to develop sophisticated systems of mathematics and philosophy. Their contributions show that the quest to understand universal patterns is a shared human endeavor, one that transcends time and geography. What's truly remarkable is how many of these ancient insights align with modern science. The Greeks' idea of a harmonious cosmos echoes our understanding of the laws of physics, while the Mayans' precise astronomical calculations mirror the accuracy of modern telescopes. Even the concept of the music of the spheres, an ancient belief that celestial bodies produce harmonic sounds, finds a modern counterpart in the study of gravitational waves, ripples in space-time that some scientists describe as the sounds of the universe. These parallels aren't just coincidences, they're evidence of a deep, intuitive understanding of the patterns that shape reality. So, as we marvel at the achievements of modern science, it's worth remembering that we stand on the shoulders of giants. The ancient Greeks, Mayans, and countless other civilizations laid the foundation for our exploration of the cosmos, showing us that the universe's patterns are not just something to be studied, they are something to be lived and experienced. And as we continue to build on their insights, we're reminded that the quest to understand the universe is as much about looking back as it is about looking forward. What other ancient wisdom might guide us as we explore the mysteries of space and time? That's where our journey takes us next, into the ways these timeless patterns continue to shape our understanding of the cosmos. As we stand at the crossroads of ancient wisdom and modern science, it's remarkable to see how far we've come in deciphering the universal patterns that shape our reality. The insights of early civilizations like the Greeks' mathematical harmony or the Mayans' celestial precision laid the groundwork for today's scientific breakthroughs. But what they could only glimpse through observation and intuition, we now explore with cutting-edge tools and technologies, uncovering layers of complexity that were once unimaginable. From the tiniest particles to the farthest reaches of the cosmos, modern science is revealing a universe far richer and more intricate than our ancestors could have dreamed. Take the standard model of particle physics, for instance. This framework, which describes the fundamental particles and forces that make up the universe, is one of the most profound achievements of modern science. It's like a periodic table for the building blocks of reality, detailing everything from quarks and electrons to the forces that bind them together. The standard model doesn't just explain the behavior of particles, it reveals the underlying symmetry and order that govern their interactions. And while it's not the final word, there are still mysteries like dark matter and quantum gravity to solve. It's a testament to how far we've come in understanding the patterns that underpin existence. Equally groundbreaking is the discovery of exoplanets, planets orbiting stars beyond our solar system. For centuries, we wondered if other worlds like ours existed, but it wasn't until the 1990s that we found the first definitive evidence. Since then, the search for exoplanets has exploded, with thousands now confirmed, ranging from rocky, Earth-like worlds to gas giants larger than Jupiter. These discoveries aren't just exciting for their own sake, they're reshaping our understanding of how planetary systems form and evolve. Each new exoplanet adds a piece to the puzzle, helping us see the broader patterns of star and planet formation across the cosmos. But it's not just about finding new worlds, it's about understanding how they fit into the larger tapestry of the universe. For example, the discovery of hot Jupiters, gas giants that orbit extremely close to their stars, challenged our previous assumptions about planetary systems. These findings forced scientists to rethink how planets migrate and interact within their systems, revealing a dynamic and ever-changing universe. Similarly, the study of exoplanet atmospheres is opening up new frontiers, allowing us to detect the chemical signatures of distant worlds and even search for signs of life. It's a reminder that the patterns of the cosmos aren't static, they're constantly evolving, offering new mysteries to unravel. And then there's cosmology, the study of the universe as a whole. Modern telescopes and observatories, like the Hubble Space Telescope and the James Webb Space Telescope, have given us unprecedented views of the cosmos, revealing galaxies billions of light-years away and capturing the faint glow of the cosmic microwave background. These observations have allowed us to map the large-scale structure of the universe, uncovering the cosmic web of galaxies and voids that stretches across the cosmos. But they've also raised new questions, like the nature of dark energy and the ultimate fate of the universe. Each discovery peels back another layer of the cosmic onion, revealing deeper patterns and connections. What's truly fascinating is how these modern discoveries build on the foundations laid by ancient civilizations. The Greeks' belief in a harmonious cosmos finds its echo in the symmetries of the Standard Model, while the Mayans' celestial precision is mirrored in our ability to map the universe's structure. Even the ancient idea of the music of the spheres resonates in the ripples of gravitational waves, the cosmic sounds that carry the stories of black holes and neutron stars. It's as if the universe has been whispering its secrets to us all along, and we're finally learning how to listen. As we continue to explore these patterns, one thing is clear: the universe is far more complex and interconnected than we ever imagined. And with each new discovery, we're reminded that the quest to understand the cosmos is a journey without end. What other secrets might the universe hold? What new patterns will we uncover as we push the boundaries of science and technology? These are questions that drive us forward, fueling our curiosity and inspiring us to keep exploring. And as we do, we're not just unraveling the mysteries of the cosmos. We're discovering more about ourselves and our place in the grand tapestry of existence. As we look to the future, the quest to unravel the universe's patterns is far from over. In fact, it feels like we're standing on the edge of a new frontier, one filled with tantalizing possibilities and unanswered questions. What if the next generation of telescopes, detectors, and quantum computers could unlock secrets we've only begun to imagine? The tools we're developing today, like the James Webb Space Telescope, the Vera Rubin Observatory, and even quantum computing, are poised to revolutionize our understanding of the cosmos, offering insights that could fundamentally reshape how we see reality itself. One of the most exciting areas of exploration is the search for dark matter. Despite making up about 27% of the universe, dark matter remains one of the greatest mysteries in physics. We know it's there because of its gravitational effects, but we still don't know what it's made of. Could it be a new type of particle, one that interacts so weakly with ordinary matter that it's nearly impossible to detect? Or is it something even more exotic, like tiny primordial black holes? Future experiments, like the Large Hadron Collider's upgrades or underground detectors searching for faint signals, might finally provide answers. Solving the dark matter puzzle wouldn't just fill a gap in our knowledge, it could rewrite the rules of physics and reveal entirely new patterns woven into the fabric of the universe. Another frontier lies in the unification of the fundamental forces. For decades, scientists have dreamed of a theory of everything, a single framework that unites the four forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. While general relativity beautifully explains the large-scale structure of the cosmos, and quantum mechanics governs the behavior of particles, the two theories don't play nicely together. Bridging this gap, perhaps through string theory, loop quantum gravity, or another yet-to-be-discovered framework, could unlock a deeper understanding of how the universe's patterns emerge from its most fundamental building blocks. Imagine a world where we can describe the birth of a star, the collision of black holes, and the behavior of subatomic particles with a single, elegant equation. It's a bold vision, but one that could transform our understanding of reality. Quantum computing, too, holds immense promise for exploring universal patterns. Unlike classical computers, which process information in binary bits, quantum computers use qubits that can exist in multiple states at once. This allows them to perform complex calculations at speeds unimaginable with today's technology. In the realm of cosmology, quantum computers could simulate the early universe with unprecedented precision, helping us understand how the first galaxies formed or how quantum fluctuations in the Big Bang gave rise to the cosmic web. They might even help us decode the behavior of black holes or simulate the elusive quantum gravity effects that occur at the tiniest scales. The potential applications are as vast as the universe itself, offering new ways to explore the patterns that define existence. But as we push the boundaries of science and technology, we're also reminded of something profound. These universal patterns aren't just abstract concepts, they connect us to the cosmos in ways that go beyond science. From the Fibonacci spirals in a sunflower to the gravitational waves rippling through space-time, the same principles that govern the universe also shape our world and our lives. They remind us that we're not separate from the cosmos, we're part of it, woven into its intricate tapestry. And as we continue to explore these patterns, we're not just uncovering the secrets of the universe, we're discovering more about ourselves and our place in the grand scheme of existence. So, what lies ahead? Perhaps the most exciting possibility is that the future will bring discoveries we can't even imagine yet. New technologies, unexpected breakthroughs, and fresh perspectives could reveal patterns we've never seen, reshaping our understanding of reality in ways that inspire awe and wonder. The universe is vast, mysterious, and endlessly creative, and as we continue to explore its patterns, we're reminded that the journey is as important as the destination. What new stories will the cosmos tell us? What new patterns will we uncover? The answers are out there, waiting to be discovered, and the adventure is just beginning. When we look up at the night sky, it's easy to feel small, a tiny speck in an unimaginably vast cosmos. But what if, instead of feeling insignificant, we saw ourselves as intricately connected to the universe? The patterns that shape the cosmos' symmetry, fractals, scaling laws aren't just abstract concepts. They're woven into the very fabric of existence, including our own lives. From the spirals of galaxies to the branching of trees, these universal rhythms remind us that we're not separate from the universe. We're an integral part of its grand design. This realization isn't just a scientific insight, it's a deeply philosophical and spiritual one, offering a profound sense of connection to the cosmos. Consider the way nature mirrors the universe's patterns. The veins of a leaf, for example, follow fractal geometry, branching in ways that echo the cosmic web of galaxies. Even the human body reflects these universal rhythms. The golden ratio, a mathematical relationship found throughout nature, appears in the proportions of our limbs and the spirals of our DNA. These patterns aren't just coincidences, they're evidence of a shared blueprint, a cosmic language that binds everything together. Recognizing these connections can inspire a sense of awe, reminding us that we're not just observers of the universe, we're participants in its ongoing story. This perspective also invites us to think about our place in the cosmos in a new way. Philosophers and spiritual thinkers have long pondered the idea of unity, the notion that all things are interconnected. Modern science, with its discoveries of universal patterns, offers a new lens through which to explore this ancient idea. When we see the same mathematical principles governing everything from the tiniest particles to the largest galaxies, it's hard not to feel a sense of wonder and humility. These patterns remind us that the universe isn't just something out there, it's something we're deeply embedded in, a living, evolving tapestry that includes us all. But this connection isn't just about awe, it's also about curiosity. Understanding universal patterns can spark a desire to learn more, to explore the mysteries of the cosmos and our place within it. It's a reminder that science isn't just about answering questions, it's about asking new ones. Why do these patterns exist? How do they shape the universe and us? These questions don't just deepen our understanding of the cosmos, they also enrich our sense of wonder, keeping the flame of curiosity alive. And here's where the connection becomes deeply personal. These universal patterns don't just exist in the stars or the quantum realm, they influence our everyday lives in ways we might not even realize. The Fibonacci sequence, for example, appears in the way plants grow, the way storms spiral, and even the way art and music are structured. Recognizing these patterns can transform the way we see the world, turning the ordinary into the extraordinary. A walk in the park becomes a journey through fractal geometry, and a glance at the night sky becomes a glimpse into the cosmic web. This shift in perspective isn't just enlightening, it's empowering, reminding us that the universe's patterns are as much a part of us as they are of the cosmos. So, as we marvel at the beauty and complexity of universal patterns, we're reminded that they're not just something to study, they're something to live by. They connect us to the cosmos, to each other, and to the deeper rhythms of existence. And as we continue to explore these patterns, we'll see how their influence extends far beyond the stars, shaping the way we think, feel, and interact with the world around us. What other insights might these patterns reveal about our place in the universe? That's where our journey continues, into the ways universal rhythms shape not just the cosmos, but our everyday lives. The patterns that govern the cosmos aren't confined to distant galaxies or the quantum realm, they're woven into the fabric of our everyday lives. From the natural world to the technologies we rely on, these universal rhythms shape the world around us in ways that are both profound and practical. Consider the branching of a river, for instance. As water flows downhill, it carves pathways that follow fractal geometry, creating intricate networks of tributaries and streams. This natural design isn't just beautiful, it's efficient, ensuring that water is distributed evenly across the landscape. The same branching pattern appears in the roots of trees, the veins in leaves, and even the structure of our own circulatory systems. It's as if nature has a blueprint, one that repeats itself across scales, from the smallest organisms to the largest ecosystems. Technology, too, is deeply influenced by these universal patterns. Take the internet, for example. At first glance, it might seem like a chaotic web of connections, but beneath the surface lies a highly organized structure. The internet's design follows a fractal-like pattern, with smaller networks branching off from larger ones, creating a system that's both robust and adaptable. This same principle is used in the design of computer chips, where circuits are arranged in branching patterns to maximize efficiency and minimize energy use. Even algorithms, the invisible engines that power everything from search engines to social media, often rely on mathematical patterns like recursion and symmetry to process information quickly and accurately. These technologies aren't just tools, they're reflections of the same universal principles that shape the natural world. But why do these patterns appear so consistently, from rivers to routers? One reason is their efficiency. Nature has had billions of years to refine its designs, and evolution favors patterns that optimize resources and energy. In technology, engineers and designers often mimic these natural solutions, borrowing from the patterns that have proven successful over millennia. This approach, known as biomimicry, has led to innovations like self-cleaning surfaces inspired by lotus leaves, or wind turbines modeled after the fins of humpback whales. By recognizing and replicating these universal patterns, we're not just solving problems, we're tapping into a deeper understanding of how the universe works. And then there's the human body, a living testament to these universal rhythms. From the spiral of our DNA to the fractal branching of our lungs, the patterns that define the cosmos are also embedded in our biology. The Fibonacci sequence, for instance, appears in the arrangement of our teeth, the proportions of our limbs, and even the way our hair grows. These patterns aren't just aesthetic, they're functional, ensuring that our bodies operate efficiently and harmoniously. When we look in the mirror, we're not just seeing ourselves, we're seeing the universe's patterns reflected back at us. Recognizing these connections doesn't just deepen our appreciation of the world, it also changes the way we see ourselves. We're not separate from the cosmos, we're an integral part of its grand design, shaped by the same forces that govern everything from galaxies to rivers. This realization can inspire a sense of awe and wonder, reminding us that the universe's patterns are as much a part of us as they are of the stars. And as we continue to explore these rhythms in nature, technology, and our own bodies, we'll uncover even more ways they shape our lives and our understanding of the world. What other secrets might these universal patterns hold, and how might they guide us toward a deeper connection with the cosmos? That's where our journey continues, into the intricate ways these rhythms influence not just the universe, but our very existence. The human body is more than just a biological marvel. It's a living, breathing reflection of the universe's patterns. From the intricate branching of blood vessels to the elegant spirals of DNA, our bodies are microcosms of the same rhythms that shape galaxies and stars. These patterns aren't just coincidental, they're evidence of a shared blueprint, a universal language that connects the smallest structures to the largest. When we look closely at the human body, we're not just seeing biology, we're seeing the cosmos in miniature. Take the circulatory system, for example. The network of arteries, veins, and capillaries that deliver oxygen and nutrients throughout the body follows a fractal pattern, branching into smaller and smaller pathways in a way that mirrors the cosmic web of galaxies. This branching isn't just efficient, it's a testament to how nature optimizes space and resources. Just as gravity pulls matter into filaments and clusters across the universe, the body's circulatory system ensures that every cell, no matter how remote, is connected to the whole. It's a reminder that the same principles of connection and distribution apply whether we're talking about blood flow or the flow of energy in the cosmos. Then there's DNA, the molecule that carries the instructions for life. At its core, DNA is a double helix, a spiral structure that echoes the forms we see in galaxies, seashells, and even weather systems. This spiral isn't just aesthetically pleasing, it's functional, allowing DNA to store vast amounts of information in a compact form. The same mathematical principles that govern the spirals of galaxies, like the Fibonacci sequence, are at work in the structure of DNA, creating a bridge between the microscopic and the cosmic. It's as if the universe has embedded its patterns into the very code of life, but the parallels don't stop there. Consider the human brain, a network of billions of neurons that communicate through intricate pathways. These neural networks, much like the cosmic web, form a vast, interconnected system where information flows in patterns that are both complex and efficient. The brain's ability to process and store information mirrors the way the universe organizes matter and energy, suggesting that the same principles of organization and connectivity apply across scales. Whether it's the firing of neurons or the collision of stars, the universe seems to favor patterns that maximize efficiency and adaptability. These biological echoes of universal patterns highlight a profound truth: life and the cosmos are deeply interconnected. The same forces that shape galaxies and stars also shape our bodies, from the branching of our veins to the spirals of our DNA. This interconnectedness isn't just a scientific observation, it's a reminder that we're part of something much larger, a cosmic tapestry that spans from the quantum realm to the farthest reaches of space. And if these patterns are woven into our bodies, could they also shape our minds? The way we think, feel, and perceive the world might be influenced by the same rhythms that govern the universe. From the way our brains process information to the way we create art and music, these universal patterns could be the invisible threads that connect us to the cosmos. It's a thought that invites us to explore not just the outer reaches of space, but the inner landscapes of our own consciousness. What other secrets might these patterns reveal about who we are and our place in the universe? That's where our journey continues into the mind, where the cosmos and consciousness meet. The human mind is a remarkable pattern recognition machine, constantly sifting through the chaos of sensory input to find order and meaning. From the moment we're born, we're wired to detect patterns, whether it's the familiar contours of a parent's face or the rhythmic cadence of a lullaby. This ability isn't just a survival mechanism, it's the foundation of how we understand and interact with the world. Think about the way we recognize faces in a crowd, solve puzzles, or even navigate complex social situations. These tasks all rely on our brain's ability to identify, process, and interpret patterns, turning raw data into meaningful insights. But pattern recognition goes beyond basic perception. It's at the heart of creativity and innovation. When artists paint, musicians compose, or scientists hypothesize, they're drawing on their ability to see connections between seemingly unrelated ideas. Take, for example, the way Leonardo da Vinci studied the flight of birds to design his early flying machines. By recognizing patterns in nature, he was able to imagine possibilities that had never been explored before. This same process drives modern innovation, from the algorithms that power artificial intelligence to the architectural designs inspired by natural forms. Creativity, at its core, is about seeing patterns where others see chaos and using those connections to create something new. What's truly fascinating is how understanding these universal patterns can enhance our cognitive abilities. Studies have shown that training the brain to recognize patterns, whether through puzzles, music, or even meditation, can improve memory, problem-solving skills, and even emotional resilience. For instance, learning to play a musical instrument strengthens the brain's ability to detect patterns in sound, which can translate to better spatial reasoning and mathematical skills. Similarly, practicing mindfulness can help us become more attuned to the patterns in our thoughts and emotions, leading to greater self-awareness and mental clarity. These benefits aren't just academic, they're practical tools for navigating the complexities of everyday life. And it's not just individuals who benefit from pattern recognition, entire societies are shaped by it. From the architectural layouts of ancient cities to the algorithms that govern modern social media, the patterns we recognize and prioritize influence how we organize and interact with the world. Consider the way urban planners design cities to mimic natural ecosystems, creating green spaces and transportation networks that mirror the efficiency of nature. Or think about how economic systems are built around patterns of supply and demand, shaping the flow of resources and opportunities. These societal structures are, in many ways, reflections of the universal patterns we've come to understand and rely on. As we explore the cognitive connections between the mind and universal patterns, we're reminded that these rhythms aren't just out there. They are within us, shaping how we think, create, and build. And as we continue to uncover these connections, we'll see how they extend beyond the individual, influencing the very fabric of society. What role might these patterns play in shaping the future of human civilization? That's where our journey takes us next, into the ways universal rhythms influence not just the mind, but the collective structures that define our world. Societal structures, whether sprawling cities, intricate networks of communication, or the flow of ideas, are not random. They are deeply influenced by the same universal patterns that shape galaxies, rivers, and even the human body. From the fractal growth of urban areas to the web-like structure of social media, these systems reflect the underlying principles of space-time, revealing how the cosmos's rhythms are embedded in the very fabric of human civilization. It's as if the universe has left its fingerprints on how we organize, connect, and evolve as a species. Take the design of cities, for example. Urban areas often grow in fractal patterns, with smaller streets branching off from larger avenues, creating a network that mirrors the veins in a leaf or the cosmic web of galaxies. This fractal growth isn't just aesthetically pleasing, it's functional, optimizing the flow of people, goods, and information. Cities like Tokyo, with its intricate subway systems, or Paris, with its radial street layouts, are microcosms of efficiency, designed to balance density and accessibility. These patterns emerge naturally, as if guided by the same principles that govern the distribution of matter in the universe. The result is a living, breathing system that evolves over time, adapting to the needs of its inhabitants while maintaining a delicate balance between order and chaos. Similarly, the way information flows through society mirrors the interconnectedness of the cosmos. Social media platforms, for instance, are built on network structures where nodes, individual users, are connected through shared interests, relationships, or interactions. This web of connections isn't random. It follows the same principles of connectivity and scaling that we see in everything from neural networks to the distribution of galaxies. The viral spread of ideas, the clustering of communities, and the emergence of trends all reflect the universal patterns of organization and interaction that shape the universe. It's a reminder that the way we communicate and share knowledge is deeply rooted in the rhythms of existence. Even the global economy, with its complex web of trade and resources, reflects these universal patterns. Supply chains, for example, are structured like branching networks, with goods flowing from producers to consumers through a series of interconnected hubs. This system, much like the cosmic web or the branching of a tree, ensures efficiency and resilience, allowing resources to be distributed where they're needed most. When disruptions occur, like natural disasters or geopolitical events, the system adapts, rerouting flows and finding new pathways. This adaptability is a hallmark of universal patterns, which thrive on balance and flexibility. What's truly fascinating is how these societal structures aren't just shaped by the patterns of space-time, they also influence them. The way we build cities, share information, or organize economies creates feedback loops that shape our environment and, in turn, the patterns we observe. For example, urban sprawl can alter local ecosystems, while the rise of digital communication has transformed how we interact with time and space. These interactions are a testament to the dynamic relationship between human civilization and the cosmos, a dance of cause and effect that unfolds on a grand scale. As we explore these connections, we're reminded that the patterns of the universe don't just govern the stars or the quantum realm. They also shape the systems we create and the societies we build. And just as these patterns influence us, we, in turn, influence them, creating a feedback loop that binds humanity to the cosmos. But what about the natural world? How do these universal rhythms shape the ecosystems that sustain life on Earth? That's where our journey takes us next, into the intricate web of connections that define the living planet. Ecosystems are nature's ultimate balancing act, a delicate interplay of forces where life thrives through patterns as old as the universe itself. From the tiniest microbes to the towering canopy of a rainforest, every living thing is part of a finely tuned system, governed by rhythms that ensure harmony and resilience. These patterns aren't just beautiful, they are essential, maintaining the balance that allows life to flourish on Earth. Whether it's the Fibonacci sequence in the spirals of a sunflower or the fractal branching of a tree's roots, the same universal principles that shape galaxies and stars also underpin the web of life. Take the Fibonacci sequence, for example. This mathematical pattern, where each number is the sum of the two preceding ones, appears in countless forms across nature. In sunflowers, the seeds are arranged in spirals that follow this sequence, maximizing space and sunlight exposure. Pine cones, pineapples, and even the arrangement of leaves on a stem often adhere to Fibonacci numbers, creating structures that are both efficient and aesthetically pleasing. These patterns aren't random, they're the result of millions of years of evolution, fine-tuning life to make the most of available resources. It's a reminder that nature is both an artist and an engineer, weaving beauty and function into every design. But the influence of universal patterns goes beyond aesthetics. It's also the foundation of ecological balance. Predator-prey dynamics, for instance, follow cyclical patterns that regulate populations and prevent any one species from overwhelming an ecosystem. When predator numbers rise, prey populations decline, which in turn leads to a decrease in predators, allowing prey to recover. This feedback loop, a kind of cosmic dance, ensures that ecosystems remain stable over time. Without these natural rhythms, ecosystems would collapse, throwing the delicate balance of life into chaos. Nutrient cycles, too, are governed by universal patterns. The carbon cycle, for example, moves carbon through the atmosphere, plants, animals, and soil in a continuous loop. This process, driven by the interplay of photosynthesis and respiration, ensures that carbon, a building block of life, remains available for all living things. Similarly, the nitrogen cycle relies on patterns of decomposition and transformation, with bacteria playing a key role in converting nitrogen into forms that plants can use. These cycles are like the heartbeat of the planet, sustaining life through rhythms that have been perfected over billions of years. The fractal branching of trees is another striking example of how universal patterns ensure resilience. From the tiniest twigs to the largest branches, trees grow in a way that maximizes sunlight absorption and nutrient distribution. This fractal structure isn't just efficient, it's also incredibly adaptable, allowing trees to recover from damage and thrive in diverse environments. Forests, in turn, serve as the lungs of the earth, regulating the climate and supporting countless species. It's a testament to how patterns at one scale, like the branching of a tree, can have far-reaching effects, shaping the health of entire ecosystems. These patterns don't just maintain balance, they also drive the evolution of species. Over millions of years, life has adapted to the rhythms of the universe, evolving structures and behaviors that align with its patterns. From the aerodynamic shapes of birds to the camouflage of insects, evolution has harnessed universal principles to create solutions that are both elegant and effective. And as we continue to explore these connections, we'll see how the cosmos's rhythms aren't just shaping life, they're guiding its future. What other secrets might these patterns hold about the evolution of species and the destiny of life on Earth? That's where our journey continues next. Evolution is nature's grand experiment, a process driven by universal patterns that shape the tree of life in ways both profound and beautiful. From the tiniest genetic mutations to the sweeping forces of natural selection, the story of life on Earth is a testament to the rhythms that govern the cosmos. These patterns don't just create diversity, they reveal a deeper unity, a shared blueprint that connects all living things, whether it's the fractal branching of a phylogenetic tree or the surprising similarities between unrelated species. Evolution is a living tapestry woven from the threads of universal principles. One of the most striking examples of these patterns is convergent evolution, where unrelated species develop similar traits in response to similar challenges. Take the streamlined bodies of dolphins and sharks, for instance. Dolphins are mammals, while sharks are fish, yet both have evolved sleek, hydrodynamic shapes to thrive in the ocean. This isn't a coincidence, it's a reflection of the same environmental pressures shaping life in predictable ways. Even more fascinating are the wings of bats and birds, or the camera-like eyes of octopuses and humans. These examples show that evolution isn't just random, it follows certain rules, guided by the patterns of space-time and the constraints of physics. It's as if the universe has a playbook and life is following its script. But the patterns of evolution go beyond individual traits. They're also visible in the way species diverge and diversify over time. Phylogenetic trees, which map the evolutionary relationships between species, often resemble fractal branching patterns, with smaller branches splitting off from larger ones in a process that mirrors the growth of trees or the structure of galaxies. These trees aren't just diagrams, they're snapshots of life's history, showing how species adapt, evolve, and sometimes go extinct. Each branch represents a unique path, shaped by the interplay of genetic variation and environmental pressures. Yet, despite their diversity, all these branches are connected, tracing back to a common ancestor, a reminder of the unity that underpins life's incredible diversity. At the heart of this process is the role of genetic mutations, the tiny, random changes that provide the raw material for evolution. While mutations might seem like chaos, they're actually part of a larger pattern of trial and error. Over millions of years, beneficial mutations are preserved through natural selection, while less advantageous ones are weeded out. This process isn't just about survival, it's about adaptation, as species evolve to fit their environments like pieces in a cosmic puzzle. The result is a living, breathing testament to the power of patterns, as life finds new ways to thrive in an ever-changing universe. What's truly remarkable is how these evolutionary patterns echo the rhythms of the cosmos itself. Just as galaxies form clusters and superclusters, species group into families and ecosystems, each one shaped by the forces that surround it. The same principles of organization and adaptation that govern the universe also guide the evolution of life, creating a seamless connection between the micro and the macro. It's a reminder that the story of life isn't separate from the story of the cosmos. It's part of the same narrative, written in the language of patterns. As we explore these connections, we're reminded that evolution isn't just a process, it's a journey, one that's shaped by the same universal rhythms that guide the stars and galaxies. And just as these patterns have shaped the history of life on Earth, they've also shaped the history of the universe itself. From the formation of the first atoms to the birth of galaxies, the cosmos has been evolving alongside life, driven by the same underlying principles. What other stories might these universal patterns tell about the past, present, and future of existence? That's where our journey continues next, into the echoes of the cosmos and the patterns that define its history. The story of the universe isn't just a timeline of events, it's a symphony of patterns, each one playing a role in the grand evolution of existence. From the fiery birth of stars to the delicate emergence of life, universal rhythms have shaped the cosmos in ways that are both awe-inspiring and deeply interconnected. These patterns aren't static, they're dynamic, evolving over billions of years through a delicate interplay of feedback loops and self-organization. They're the invisible forces that have guided the universe from a hot, dense singularity to the vast, intricate web of galaxies, planets, and life we see today. Let's start with the stars, the cosmic engines that light up the universe. When the first stars formed, they weren't just random collections of gas, they were shaped by the gravitational patterns that pulled matter together into dense clumps. As these clumps collapsed under their own weight, they ignited nuclear fusion, transforming hydrogen into helium and releasing immense amounts of energy. This process didn't just create light, it set the stage for everything that followed. When these early stars died, they exploded in supernova, scattering heavier elements like carbon, oxygen, and iron across the cosmos. These elements became the building blocks for new stars, planets, and eventually, life itself. It's a cosmic recycling system, driven by patterns that repeat across time and space. But stars are just one piece of the puzzle. The formation of galaxies, vast collections of stars, gas, and dark matter, was also guided by universal patterns. As matter clumped together under gravity, it formed intricate filaments and clusters, creating the cosmic web we see today. This web isn't random, it's a reflection of the underlying structure of the universe, shaped by the interplay of gravity, dark matter, and dark energy. Over billions of years, galaxies have evolved, merging and interacting in ways that reflect these patterns. The Milky Way, for example, is on a collision course with the Andromeda Galaxy, a dance that will reshape both galaxies in a cosmic tango guided by the same forces that shaped the early universe. And then there's life, perhaps the most remarkable outcome of these universal patterns. On Earth, life emerged from the interplay of chemistry, geology, and the energy from the sun. The same elements forged in stars' carbon, nitrogen, oxygen became the foundation for the molecules that make up living organisms. Over billions of years, life evolved through a process of feedback loops and self-organization, adapting to the rhythms of the planet and the cosmos. From the first single-celled organisms to the complex ecosystems we see today, life has been shaped by the same patterns that govern the stars and galaxies. It's a reminder that we're not separate from the universe. We're part of its ongoing story. These patterns aren't just about the past, they also give us a framework for understanding the future. By studying how the universe has evolved, we can make predictions about where it's headed. Will dark energy continue to drive the expansion of the universe, eventually pulling galaxies apart? Or will gravity eventually reverse this expansion, leading to a cosmic collapse? These questions aren't just theoretical, they're rooted in the patterns we've observed throughout cosmic history. And as we continue to explore these patterns, we're reminded that the universe is a living, evolving entity, full of surprises waiting to be uncovered. But what about the smallest scales? Just as universal patterns have shaped the cosmos, they also play a crucial role in the quantum realm, where the rules of physics take on a whole new dimension. From the behavior of particles to the strange phenomena of quantum entanglement, the quantum world is governed by its own set of patterns, ones that challenge our understanding of reality itself. How do these quantum patterns connect to the larger rhythms of the universe? That's where our journey continues, into the mysterious and fascinating world of the very small. The quantum realm is where the universe's patterns take on their most mysterious and mind-bending forms. Here, the rules of classical physics break down, and the familiar rhythms of space-time give way to a world of uncertainty, duality, and interconnectedness. At this scale, particles don't behave like solid objects with fixed properties. They exist in a haze of possibilities, governed by patterns that defy our everyday intuition. From wave-particle duality to quantum entanglement, the quantum world is a place where reality itself seems to flicker, revealing a deeper layer of the cosmos's design. Wave-particle duality is one of the most iconic examples of quantum strangeness. Imagine a photon, the smallest unit of light. In some experiments, it behaves like a particle, a tiny bullet traveling in a straight line. But in others, it acts like a wave, spreading out and creating interference patterns. This duality isn't just a quirk of light, it's a fundamental feature of all quantum particles, from electrons to atoms. The double-slit experiment, where particles pass through two slits and create wave-like patterns on a screen, is a perfect illustration of this phenomenon. It's as if the universe is playing a cosmic game of hide and seek, revealing its true nature only when we're not looking too closely. But wave-particle duality is just the tip of the quantum iceberg. Quantum entanglement takes the strangeness to a whole new level. When two particles become entangled, their properties become linked, no matter how far apart they are. Measure one, and the other instantly adjusts, as if they're connected by an invisible thread. Albert Einstein famously called this spooky action at a distance, and for good reason. It seems to defy the speed of light and our classical understanding of space-time. Yet, experiments have repeatedly confirmed that entanglement is real, showing that the universe is far more interconnected than we ever imagined. What's truly remarkable is how these quantum patterns challenge our notions of reality. In the classical world, objects have definite positions and states, but in the quantum realm, particles exist in a superposition of possibilities, only collapsing into a definite state when observed. This suggests that reality isn't something fixed and independent. It's something that emerges through interaction and observation. It's as if the universe is a vast, dynamic tapestry, and we're not just passive observers but active participants in its creation. These quantum patterns also hint at a deeper structure to space-time. In classical physics, space and time are smooth and continuous, but at the quantum level, they might be granular, made up of tiny, indivisible units. This idea, known as quantum foam, suggests that space-time itself is a fluctuating, frothy sea at the smallest scales. It's a radical departure from our everyday experience, but it could hold the key to reconciling quantum mechanics with general relativity, a problem that has puzzled scientists for decades. As we explore these quantum patterns, we're not just uncovering the secrets of the universe, we're also laying the groundwork for future technologies. Quantum computing, for instance, harnesses the principles of superposition and entanglement to perform calculations at speeds unimaginable with classical computers. These machines could revolutionize fields like cryptography, materials science, and artificial intelligence, solving problems that are currently beyond our reach. Similarly, quantum sensors could detect gravitational waves or dark matter with unprecedented precision, opening new windows into the cosmos. The quantum realm is a place of endless possibilities, where the patterns of the universe reveal their most profound and mysterious forms. By understanding these patterns, we're not just learning about the cosmos, we're also discovering new ways to shape the future. What other secrets might the quantum world hold, and how might they transform our understanding of reality? That's where our journey continues, into the technologies and breakthroughs that could redefine the boundaries of science and imagination. Quantum technologies are not just futuristic concepts, they're the next frontier in our ability to harness the patterns of the universe. These groundbreaking innovations, like quantum computing and cryptography, are built on principles that might sound like science fiction, but are deeply rooted in the fabric of reality. Quantum mechanics, with its strange and counterintuitive behaviors, has given us a new set of tools to decode the universe's rhythms and apply them in ways that could transform our world. From revolutionizing medicine to securing communication, these technologies are poised to reshape entire industries, all by tapping into the patterns that govern the very smallest scales of existence. At the heart of quantum computing is the principle of superposition, the idea that a quantum bit or qubit can exist in multiple states at once. Unlike classical bits, which are either 0 or 1, qubits can be both simultaneously, allowing quantum computers to perform many calculations in parallel. This ability to process information exponentially faster than classical computers could revolutionize fields like drug discovery, where simulating molecular interactions is currently limited by the immense computational power required. Imagine being able to design life-saving medications in days rather than decades, all because we've learned to harness the quantum patterns that underpin reality. But quantum computing isn't the only game changer. Quantum cryptography, which uses the principles of quantum entanglement, offers a level of security that's virtually unbreakable. In this system, the act of measuring a quantum state alters it, meaning any attempt to intercept a message would be immediately detectable. This unhackable encryption could transform how we protect sensitive information, from financial transactions to national security. By leveraging the interconnectedness of quantum particles, we're not just improving technology, we're redefining what's possible in communication and data protection. The development of these technologies hinges on our understanding of quantum patterns. Take quantum entanglement, for example. This phenomenon, where particles become linked across vast distances, is more than just a curiosity, it's the foundation of quantum networks. By exploiting these connections, we could create a global quantum internet, enabling instant communication that's immune to hacking. It's a vision that feels almost magical, yet it's grounded in the same universal rhythms that shape everything from atoms to galaxies. What makes these advancements even more remarkable is how they echo the patterns we see in nature. Just as ecosystems rely on interconnected feedback loops to maintain balance, quantum systems thrive on the interplay of particles and forces. This harmony between the micro and macro scales is a reminder that the universe's patterns are not just abstract concepts, they're actionable insights that can shape the future of technology, and by extension, humanity itself. As we explore these quantum technologies, we're reminded that the patterns of the universe don't just exist in isolation. They influence every aspect of our lives, even the flow of time itself. Time, often thought of as a steady, unchanging force, is deeply intertwined with the rhythms of space and energy. From the way quantum particles behave to the way black holes warp spacetime, the universe's patterns shape how we experience time. How might this connection between patterns and time redefine our understanding of reality? That's where our journey takes us next, into the enigmatic relationship between universal rhythms and the fabric of time. Time is one of the most mysterious and fundamental aspects of our existence, yet it's also one of the most deeply patterned. From the steady ticking of a clock to the mind-bending effects of time dilation near a black hole, the flow of time is governed by universal rhythms that shape how we experience reality. These patterns aren't just abstract concepts, they're woven into the very fabric of the universe, influencing everything from the decay of a leaf to the expansion of galaxies. Understanding how time works isn't just about measuring seconds and minutes. It's about uncovering the deeper rhythms that connect the past, present, and future. One of the most striking patterns in time is the arrow of time, the idea that time moves in one direction, from the past to the future. Think about how a cup of coffee cools down but never spontaneously heats up, or how a broken egg can't reassemble itself. These everyday phenomena are governed by the second law of thermodynamics, which states that entropy, or disorder, always increases over time. This law gives time its direction, creating a flow that's as inevitable as it is irreversible. Without it, the universe would be a chaotic jumble of events with no clear sequence, no cause and effect, no story to tell. But entropy isn't just about disorder. It's also about the patterns that emerge from it. Take the formation of stars, for example. In the early universe, matter was scattered and uniform, a state of high entropy. But as gravity pulled matter together, forming stars and galaxies, entropy increased even further, creating structures that were more complex and ordered on a local scale. This interplay between order and disorder is a hallmark of the universe's patterns, showing how time's arrow drives both the breakdown and the creation of structure. It's a reminder that time isn't just about decay, it's also about transformation, a force that shapes the cosmos in ways we're only beginning to understand. Another fascinating aspect of time is time dilation, a phenomenon predicted by Einstein's theory of relativity. Imagine two astronauts, one stays on Earth while the other travels near the speed of light. When the traveling astronaut returns, they'll find that less time has passed for them than for their Earth-bound counterpart. This isn't science fiction, it's a real effect confirmed by experiments with atomic clocks on airplanes and satellites. Time dilation shows that time isn't a fixed, universal constant. It's a flexible, dynamic dimension that bends and stretches depending on speed and gravity. Near a black hole, for instance, time slows down so dramatically that a few minutes there could equal years elsewhere. These patterns of time dilation reveal a universe where time is deeply intertwined with space and energy, a dance of rhythms that defy our everyday experience. What's truly remarkable is how these patterns of time shape our perception of reality. The flow of time isn't just a backdrop to our lives, it's an active participant influencing how we think, feel, and experience the world. Our brains, for instance, are finely tuned to the rhythms of time, from the milliseconds it takes to process a sound to the decades that shape our memories. Even our sense of self is tied to time, as we weave our experiences into a narrative that stretches from the past into the future. Time's patterns aren't just out there, they're within us, shaping the very essence of who we are. As we explore these temporal dynamics, we're reminded that time isn't just a measure, it's a story, one that's written in the language of universal patterns. And just as these rhythms shape the flow of time, they also hint at something even more profound, the concept of infinity. What happens when we extend these patterns beyond the boundaries of time as we know it? That's where our journey takes us next, into the mysteries of infinity and the endless possibilities it holds. Infinity is a concept that stretches the limits of our imagination, a pattern that defies boundaries and challenges our understanding of space, time, and even reality itself. It's not just a mathematical abstraction or a philosophical idea, it's a fundamental feature of the universe, woven into the very fabric of existence. From the seemingly endless expanse of the cosmos to the infinite divisibility of matter, infinity is a pattern that inspires both awe and unease, forcing us to confront the limits of what we can comprehend. Consider the universe itself. When we look up at the night sky, we're not just seeing stars and galaxies, we're peering into an infinite expanse, a cosmic ocean that stretches beyond the reach of our telescopes. The observable universe, the part we can see, is already unimaginably vast, spanning over 90 billion light-years. But what lies beyond? Is the universe infinite, or does it have an edge? These questions aren't just speculative, they're rooted in the patterns we observe. From the way galaxies are distributed to the cosmic microwave background that hints at the universe's origins. Infinity, in this context, isn't just a theoretical concept, it's a pattern that shapes the very structure of the cosmos. But infinity isn't just about the vastness of space, it's also about the smallest scales of existence. Take matter, for example. At first glance, it seems solid and finite, but when we zoom in, we find a world of endless complexity. Atoms are made of protons, neutrons, and electrons, which in turn are made of quarks and gluons. And there's no reason to think the division stops there. Theories like string theory suggest that particles might be made of tiny, vibrating strings, opening up the possibility of infinite layers of structure. This idea, known as infinite divisibility, challenges our understanding of what matter really is, showing that even the smallest particles are part of a larger, infinite pattern. Infinity also plays a crucial role in our understanding of time. While we experience time as a linear flow from past to future, some theories suggest that time might be infinite, stretching endlessly in both directions. The Big Bang, often thought of as the beginning of time, might not be a true starting point but rather a transition from a previous state. Similarly, the fate of the universe, whether it will expand forever or collapse in a big crunch, raises questions about the infinite nature of time. These ideas push us to rethink not just the universe's history, but also our place within it, as creatures bound by finite lifespans in an infinite cosmos. What makes infinity so fascinating is how it challenges our intuition. We're used to thinking in terms of beginnings and endings, limits and boundaries, but infinity defies these frameworks. It's a reminder that the universe is far stranger and more complex than our everyday experience suggests. And yet, despite its elusiveness, infinity inspires a sense of wonder, inviting us to explore the patterns that lie beyond our grasp. As we grapple with the concept of infinity, we're reminded that these patterns aren't just out there, they're also within us, shaping the way we think and perceive the world. The human mind, with its capacity for abstract thought and imagination, is uniquely equipped to contemplate the infinite. From the infinite potential of creativity to the boundless depths of consciousness, infinity is a pattern that connects the cosmos to the inner workings of our minds. And as we continue this journey, we'll see how these universal rhythms extend beyond the physical world, influencing the very essence of who we are. What role might infinity play in the realm of consciousness? That's where our exploration takes us next. Consciousness is one of the most profound mysteries in the universe, a phenomenon that bridges the finite and the infinite. It's the spark that allows us to perceive, reflect, and wonder, to look up at the stars and ask, what does it all mean? But what if consciousness itself is part of the infinite patterns that shape existence? From the vastness of the cosmos to the intricate workings of the human brain, there's a growing sense that the mind and the universe are deeply interconnected, sharing rhythms and structures that hint at something far greater than we can fully grasp. Think about the brain, the most complex structure we know of in the universe. With its billions of neurons and trillions of connections, it's a fractal-like network, constantly firing and rewiring in response to the world around it. These neural patterns mirror the cosmic web of galaxies, both systems governed by principles of connectivity and efficiency. It's as if the universe has encoded its own structure into the very organ that allows us to understand it. This idea isn't just poetic, it's supported by scientific research, which suggests that the brain's architecture follows scaling laws similar to those found in galaxies and ecosystems. The patterns of the cosmos, it seems, are echoed in the patterns of thought, but the connection goes deeper. Some philosophers and scientists argue that consciousness itself might be a fundamental property of the universe, like space, time, or energy. This idea, known as panpsychism, suggests that even the smallest particles possess a form of awareness, and that human consciousness is just a more complex manifestation of this universal quality. While this theory is still speculative, it raises fascinating questions about the nature of existence. Could the universe be not just a collection of objects, but a living, aware entity? And if so, what does that mean for our understanding of infinity? Infinity, after all, isn't just about the vastness of space or the endless flow of time. It's also about the boundless potential of the mind. When we dream, create, or imagine, we're tapping into a realm of infinite possibilities, a space where the rules of the physical world no longer apply. This creative spark is what allows us to envision new worlds, solve complex problems, and explore the mysteries of existence. It's as if the mind is a microcosm of the infinite, a place where the patterns of the universe come alive in thought and imagination. These connections between consciousness and infinity aren't just abstract ideas, they are deeply personal. When we gaze at a starry sky or lose ourselves in a piece of music, we're experiencing a kind of infinity, a moment where the boundaries between self and universe seem to dissolve. These experiences inspire awe, a feeling that transcends language and logic, reminding us of our place in the grand tapestry of existence. They also raise profound questions. What is the nature of consciousness? Is it a product of the brain or something more fundamental? And how does it connect us to the infinite patterns of the cosmos? As we ponder these questions, we're reminded that the universe's patterns don't just shape the physical world, they also inspire our sense of beauty. From the symmetry of a snowflake to the spirals of a galaxy, these rhythms evoke a deep emotional response, a sense of harmony and wonder that transcends explanation. What is it about these patterns that moves us so deeply, and how do they connect to the infinite potential of the mind? These are questions that bridge science and art, philosophy and spirituality, inviting us to explore the deeper connections between the cosmos and the human experience. And as we continue this journey, we'll see how these universal rhythms don't just shape our understanding of existence, they shape our perception of beauty itself. Beauty is often said to be in the eye of the beholder, but what if it's also written into the very fabric of the universe? From the delicate symmetry of a snowflake to the sweeping spirals of galaxies, universal patterns create a kind of aesthetic harmony that transcends cultures, time, and even species. These patterns aren't just functional, they're beautiful, evoking a sense of wonder that has inspired artists, scientists, and philosophers for centuries. It's as if the cosmos is both an artist and a mathematician, weaving together form and function in ways that captivate the human spirit. Take symmetry, for example. Whether it's the hexagonal perfection of a snowflake or the radial symmetry of a sunflower, These patterns are everywhere in nature. Symmetry isn't just pleasing to the eye, it's a reflection of the underlying order of the universe, a balance that emerges from the laws of physics and mathematics. When we see a butterfly's wings or the petals of a rose, we're not just admiring their beauty, we're witnessing the same principles that govern the arrangement of stars in a galaxy or the structure of atoms. This connection between beauty and order suggests that aesthetics isn't just a human invention, it's a fundamental feature of reality. Spirals, too, are a universal motif, appearing in everything from the swirl of a hurricane to the arms of a galaxy. The Fibonacci sequence, a mathematical pattern where each number is the sum of the two preceding ones, often underlies these spirals, creating structures that are both efficient and visually stunning. In nature, this pattern can be seen in the way leaves unfurl, shells grow, or galaxies form. These spirals aren't just random, they're the result of processes that optimize space, energy, and growth. When we marvel at the spiral of a nautilus shell or the whirl of a galaxy, we're seeing beauty born from necessity, a reminder that the universe's patterns are as practical as they are poetic. But beauty isn't just about symmetry and spirals, it's also about harmony, the way different elements come together to create a unified whole. In music, for instance, harmony arises from the interplay of notes, blending them into something greater than the sum of their parts. Similarly, in the cosmos, harmony emerges from the interaction of forces, particles, and structures, creating a universe that's both diverse and cohesive. This sense of harmony is what makes the universe feel alive, a dynamic system where every part plays a role in the greater whole. What's truly fascinating is how recognizing these patterns deepens our appreciation of the universe. When we understand the mathematics behind a snowflake or the physics behind a galaxy, we don't just see beauty, we see meaning. It's as if the universe is speaking to us, revealing its secrets through the language of patterns. This connection between science and aesthetics isn't just intellectual, it's emotional, evoking a sense of awe that transcends explanation. Whether we're gazing at a starry sky or studying the intricate details of a fractal, these moments of recognition remind us that we're part of something vast, beautiful, and deeply interconnected. And this brings us to the idea of harmony, a concept that extends beyond aesthetics to encompass the very essence of existence. From the balance of ecosystems to the interplay of forces in the cosmos, harmony is the thread that weaves the universe together, creating a tapestry of order and beauty. It's a principle that resonates not just in nature, but in art, music, and even human relationships, reflecting the universal patterns that shape everything from the smallest atom to the largest galaxy. As we explore these connections, we'll see how harmony isn't just a concept, it's a reflection of the rhythms that define the cosmos itself. Harmony is the invisible force that brings order to chaos, the delicate balance that allows the universe to sing in unison. It's the resonance of musical notes blending into a melody, the equilibrium of ecosystems where every species plays a role, and the cosmic dance of galaxies bound by gravity. At its core, harmony is the result of universal patterns working together, creating a symphony of existence that stretches from the smallest particles to the vastness of space. These patterns don't just coexist, they interact, complement, and enhance one another, forming a tapestry of balance that defines the very essence of the cosmos. Take music as an example. When a musician plucks a guitar string or strikes a piano key, the sound waves produced aren't random. They're governed by mathematical relationships, frequencies that align in ways we perceive as harmonious. The octave, for instance, is a perfect doubling of frequency, creating a sound so pleasing that it's used in nearly every musical tradition around the world. These harmonic relationships aren't just beautiful, they are rooted in the physics of sound waves, the same principles that govern the vibrations of particles and the resonance of stars. It's as if the universe has embedded its rhythms into the very fabric of music, allowing us to hear the patterns that shape existence. But harmony isn't limited to sound, it's also visible in the natural world. Ecosystems are a perfect example of this balance. In a healthy forest, every organism, from the tallest tree to the tiniest microbe, plays a role in maintaining the system's equilibrium. Predators keep prey populations in check, plants absorb carbon dioxide and release oxygen, and decomposers recycle nutrients back into the soil. This intricate web of interactions creates a self-sustaining harmony, one that's resilient and adaptable. When one element is disrupted, the entire system feels the ripple, a reminder of how deeply interconnected life truly is. These patterns of balance aren't just a feature of ecosystems, they're a reflection of the universal principles that govern the cosmos. In the cosmos itself, harmony takes on a grander scale. The orbits of planets, the fusion of stars, and the collisions of galaxies are all governed by the interplay of forces, creating a cosmic balance that's both dynamic and enduring. Gravity, for instance, pulls matter together, while the expansion of space-time pushes it apart. This delicate tension shapes the structure of the universe, from the spiral arms of galaxies to the cosmic web of filaments and voids. It's a reminder that harmony isn't about stillness, it's about the dynamic interplay of opposing forces, a dance that's as old as the universe itself. What makes these patterns of harmony so profound is how they connect us to the cosmos. When we recognize the balance in a musical chord, the resilience of an ecosystem, or the symmetry of a galaxy, we're not just observing the universe, we're participating in its rhythms. This sense of unity isn't just intellectual, it's deeply emotional, evoking a feeling of connection that transcends language and culture. It's as if the universe is reminding us that we're part of something larger, a grand design that's both beautiful and meaningful. But harmony isn't just something we observe, it's something we can cultivate. By understanding these universal patterns, we can create balance in our own lives, whether it's through mindful living, sustainable practices, or artistic expression. The same principles that govern the cosmos can guide our relationships, our communities, and our planet, fostering a sense of unity and purpose. And as we continue to explore these patterns, we'll see how they shape not just the universe, but also the concept of interconnectedness, the idea that everything is woven together in an intricate web of existence. What deeper truths might this interconnectedness reveal about the cosmos and about ourselves? That's where our journey takes us next. Interconnectedness is the thread that weaves the universe together, binding everything from the tiniest quantum particles to the vast cosmic web in a single, intricate tapestry. These universal patterns aren't isolated phenomena, they are the echoes of a deeper unity, a harmony that transcends scale and time. Whether it's the delicate flutter of a butterfly's wings influencing weather patterns halfway across the globe, or the sprawling network of galaxies connected by filaments of dark matter, the cosmos is a living testament to how deeply interconnected all things truly are. Consider the butterfly effect, a concept from chaos theory that shows how small changes can lead to vastly different outcomes. The idea is simple. A butterfly flapping its wings in Brazil could set off a chain reaction of atmospheric events, eventually leading to a tornado in Texas. This isn't just a poetic metaphor, It's a scientific principle that reveals how interconnected and sensitive the universe is to even the smallest actions. Every event, no matter how minor, ripples through the fabric of reality, influencing the course of existence in ways we can't always predict. It's a reminder that no part of the universe exists in isolation. Every piece is part of a larger, dynamic whole. On a grander scale, the cosmic web illustrates this interconnectedness in breathtaking detail. Picture the universe as a vast network, with galaxies clustered along filaments of dark matter, stretching across billions of light years. These filaments aren't random, they're the result of gravity's pull, drawing matter together into a structure that looks remarkably like the neural networks in our brains or the branching veins of a leaf. This cosmic architecture shows that the same patterns repeat across scales, from the microscopic to the universal. It's as if the universe is echoing its own design, reminding us that everything is part of a single, unified system. But interconnectedness isn't just about physical structures, it's also about energy and information. In the quantum realm, particles can become entangled, their properties linked across vast distances in ways that defy classical physics. When one particle is measured, the other instantly responds, as if they're communicating faster than the speed of light. This phenomenon, known as quantum entanglement, reveals a level of connection that challenges our understanding of space and time. It suggests that the universe operates as a seamless whole, where boundaries between objects are more fluid than we once thought. These quantum connections are a microcosm of the larger unity that defines the cosmos. What's truly inspiring about these patterns is how they highlight the unity of existence. From the smallest atom to the largest galaxy, the universe is a single, interconnected system, shaped by the same fundamental principles. This interconnectedness isn't just a scientific observation, it's a profound truth that resonates on a deeply human level. It reminds us that we're not separate from the cosmos, we're part of it, shaped by the same rhythms and forces that govern everything from stars to cells. This realization can inspire a sense of awe and wonder, inviting us to see ourselves not as isolated individuals, but as participants in a grand, cosmic dance. As we explore these universal patterns, we're reminded that they don't just reveal the interconnectedness of all things, they also spark curiosity and imagination. The more we learn about the cosmos, the more questions arise, drawing us deeper into the mysteries of existence. What other connections might we uncover as we continue to explore the universe? How might these patterns shape our understanding of ourselves and our place in the cosmos? These are questions that keep us searching, pushing the boundaries of knowledge and wonder. And as we continue this journey, we'll see how these universal rhythms not only connect us to the cosmos, but also inspire us to reach beyond what we know, into the infinite possibilities of the unknown. Throughout history, the patterns woven into the fabric of the universe have sparked a profound sense of wonder and curiosity in the human spirit. These rhythms, whether in the spirals of galaxies, the symmetry of snowflakes, or the branching of trees, have not only shaped our understanding of the cosmos, but also driven our relentless pursuit of knowledge. They are the silent whispers that beckon us to explore, to question, and to dream. From the earliest stargazers to the cutting-edge scientists of today, universal patterns have been the compass guiding humanity's quest to unravel the mysteries of existence. In the realm of science, these patterns have been a source of inspiration and revelation. Think of Johannes Kepler, who, captivated by the harmony of planetary motion, discovered the laws that govern the orbits of planets. His work was rooted in the belief that the universe operates according to elegant, mathematical principles. a belief that continues to drive scientific inquiry today. Similarly, the discovery of the double helix structure of DNA, with its spiraling elegance, revealed the universal patterns that underpin the code of life. These breakthroughs remind us that the cosmos is not just a chaotic jumble of matter and energy. It's a symphony of order waiting to be deciphered. But universal patterns don't just fuel scientific discovery, they also inspire artistic expression. Artists, musicians, and writers have long drawn from the rhythms of the cosmos to create works that resonate with beauty and meaning. The golden ratio, for example, has been used for centuries to craft visually pleasing compositions, from the architecture of the Parthenon to the paintings of Leonardo da Vinci. In music, the Fibonacci sequence often underpins the structure of compositions, creating harmonies that feel both natural and transcendent. These creative expressions are more than just art, they're a dialogue with the universe, a way of translating its patterns into something that speaks to the human soul. What's truly remarkable is how these patterns remind us of the mysteries that still await exploration. For all that we've learned about the cosmos, there's so much we don't yet understand. Dark matter and dark energy, the nature of consciousness, the true origins of the universe, these are questions that continue to challenge and inspire us. Universal patterns are like signposts, pointing us toward the unknown and inviting us to keep searching. They remind us that the universe is not a puzzle to be solved, but a story to be discovered, one that unfolds with each new insight and revelation. As we reflect on the legacy of universal patterns, it's clear that they are more than just scientific curiosities or artistic inspirations. They are a testament to the interconnectedness of all things. They remind us that we are part of something vast, beautiful, and deeply mysterious. Whether we're gazing at the stars, studying the structure of a leaf, or creating a work of art, we're engaging with the same rhythms that shape the cosmos. These patterns are a bridge between the known and the unknown, the finite and the infinite, the physical and the spiritual. In this journey through the 40 universal patterns, we've explored how they shape everything from the quantum realm to the cosmic web, from the flow of time to the evolution of life. We've seen how they inspire wonder, drive discovery, and connect us to the universe in profound ways. But perhaps the most important lesson is this: the universe's patterns are not just out there, they are within us, shaping how we think, create, and experience the world. And as long as we remain curious, as long as we keep asking questions, we'll continue to uncover the secrets they hold, one rhythm at a time. As we reach the end of this cosmic journey, it's time to step back and marvel at the 40 universal patterns that weave through the fabric of space-time. These patterns, whether in the spirals of galaxies, the symmetry of snowflakes, or the quantum dance of particles, are far more than just abstract concepts. They are the hidden rhythms of existence, the silent forces that shape everything from the smallest atom to the vast expanse of the cosmos. Together, they form a symphony of order and complexity, revealing a universe that is deeply interconnected, endlessly dynamic, and profoundly beautiful. What makes these patterns so extraordinary is how they transcend scale and time. From the branching of a tree to the filaments of the cosmic web, the same principles of organization and balance repeat across the universe. They show us that the cosmos isn't a collection of isolated phenomena, it's a unified system where every part is linked to the whole. Even the tiniest quantum fluctuation can ripple out to shape the grandest structures, reminding us that nothing exists in isolation. These patterns are the universe's way of speaking to us, offering clues about its origins, its structure, and its future. But understanding these patterns isn't just about science, it's about transformation. When we grasp the elegance of a fractal, the harmony of a spiral, or the balance of an ecosystem, we begin to see the world differently. The chaos of everyday life takes on a new order, revealing the deeper rhythms that connect us to the cosmos. Suddenly, the night sky isn't just a scattering of stars. It's a story written in the language of universal patterns, and we, as part of this grand narrative, are both observers and participants, shaped by the same forces that guide the stars. This shift in perspective is more than intellectual, it's deeply personal. It reminds us that we're not separate from the universe. We're woven into its fabric, shaped by its patterns and rhythms. Whether it's the Fibonacci sequence in a sunflower or the gravitational waves from colliding black holes, these patterns are part of us, echoing in our bodies, our thoughts, and our creations. They inspire us to dream, to explore, and to imagine what lies beyond the limits of our understanding. As we close this exploration, let's reflect on the words of Carl Sagan, who once said, "Somewhere, something incredible is waiting to be known." The 40 universal patterns are a reminder that the universe is full of mysteries waiting to be uncovered, each one a thread in the cosmic tapestry. They invite us to keep asking questions, to keep searching, and to keep marveling at the beauty and complexity of existence. So, what do you think? How do these patterns shape your understanding of the cosmos? Share your thoughts in the comments below. I'd love to hear your perspectives. And if you've enjoyed this journey through the fabric of space-time, don't forget to subscribe for more cosmic explorations. Together, let's continue to unravel the mysteries of the universe, one